Today we're diving into one of the most profound books of the 20th century, A Brief History of Time by the legendary Stephen Hawking.
It really is a foundational text. It's that book that sat on millions of coffee tables, often, maybe not fully read. But today, we're actually going to do the heavy lifting.
We're cracking it open.
We are. We're going to get in there and see what makes it tick. And it's not just about, physics equations. We're tracing the evolution of humanity's our entire picture of the universe.
I am so ready to have my mind bent. But before we get completely lost in the stars, I do have a special welcome for everyone listening. Welcome to Fact Horizon. This is where history meets mystery and facts define the future. We explore the profound truths of human existence, the wonders of the mind, and the secrets of the cosmos, all in one place. If you seek knowledge and wonder, you're in the right spot. Subscribe now and join our journey beyond the horizon.
Beyond the horizon is actually the perfect way to frame this. Because for most of human history, the horizon was literally the limit of our world. Hawking's book is all about smashing past that limit again and again.
So lay out the mission for us today. We're covering part one, which is the first two chapters of the book. What's the narrative arc we're following here?
Okay, so our objective is to track this incredible intellectual journey. We're going from, and this is a real thing, the ancient idea of a flat Earth supported by a stack of tortoises. The turtles, all the way to the mind-bending concepts of general relativity and the warping of space-time itself. We're going to see how we got from Aristotle to Newton, and then the really big jump for Newton to Einstein.
Okay.
It's really the story of how our comfortable, static, reliable universe got completely replaced by something dynamic, expanding, and fundamentally strange.
Okay, let's unpack this, and I want to start exactly where Hawking starts with the story. It's an anecdote that, honestly, it cracks me up every time, but I think it serves a really serious philosophical point.
Oh, it absolutely does. It sets the whole stage for the problem of knowledge. How do we know what we know?
So the story goes, and Hawking suggests it might have been Bertrand Russell, though nobody's 100% sure,
Right.
that a well-known scientist is giving a public lecture on astronomy. He's up there, describing how the Earth orbits the sun and how our sun orbits the center of this huge collection of stars we call our galaxy. He's laying out the whole modern view.
And of course, at the end of the lecture, this little old lady at the back of the room gets up, and she is not impressed.
Not impressed at all. She basically stands up and says, "What you have told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise."
It's such a wonderfully absurd image. And the scientist, you can imagine him kind of smiling, probably a bit smugly, and he decides to dismantle her with just one question.
Yeah, he asks, "And what is the tortoise standing on?"
And she just shoots back, doesn't miss a beat. "You're very clever, young man. Very clever. But it's turtles all the way down."
It's a great punchline.
It is. But Hawking's point isn't just to make us laugh at her. He asks this really uncomfortable question right after. Why do we think we know any better?
And that's the kicker. I mean, I've never been to space. I haven't personally, calculated the orbit of the moon or anything. I'm just trusting the scientists in the same way she was trusting her turtles.
Exactly. Most of us, we operate on models that are handed down to us. The turtle tower is a mental model. It explains why the Earth doesn't fall. It's supported. It fits our intuition that the ground feels flat. So the real question becomes, what evidence is strong enough to force us to throw out an old model and build a new one?
Okay, so let's go back to that first big model update. We have to go way, way back. We're talking 340 BC, Aristotle.
Aristotle. Yeah, we have this common misconception that, everybody before Columbus thought the Earth was flat. It's just not true. The ancient Greeks, and Aristotle in particular, had already figured out the Earth was a sphere.
And they did it without satellites, without telescopes.
Pure logic and observation, just looking up and thinking.
I love this part because the arguments are so accessible. These are things you could go out and verify tonight.
You absolutely could. So Aristotle had a few key arguments. The first one involved the moon. He would watch lunar eclipses. That's when the Earth passes between the sun and the moon, and our shadow falls on the moon's surface.
And he just looked at the shape of that shadow.
He looked at the shape, and he noticed that the edge of the shadow was always round. It was always a curve.
Now, just to play devil's advocate for a second, if the Earth were a flat disk, like a frisbee, couldn't it cast a round shadow?
It could, but only under very specific circumstances. Like if the eclipse always happened when the sun was directly underneath the center of the disk. But eclipses happen at all different angles and times. If the Earth were a flat disk, Sooner or later, you'd see a shadow that looked like a long, thin ellipse, or even just a straight line.
But that never happened.
Never. The shadow was always round. And the only object that casts a perfectly round shadow from every single angle is a sphere.
It's brilliant. It's a geometric proof you can see with your naked eye. Okay, so what was his second argument?
The second was all about travel. The Greeks were seafarers. They sailed all over the Mediterranean, and they noticed that when they traveled south, say from Greece down to Egypt, the North Star appeared lower in the sky.
Lower relative to the horizon.
Yes. If the Earth were flat, the North Star is so far away that it should look like it's at the same height no matter where you are. But because the Earth is curved, as you move south, you are physically moving over that curve, and your viewing angle to the north changes.
And he even used that observation to estimate the size of the Earth, right?
He did. He quoted an estimate of 400,000 stadia. Now, we're not exactly sure how long a stadium was, but best guesses put his estimate at maybe double the correct size, which for 340 BC is just astonishingly good.
And there was a third piece of evidence, too, wasn't there? The one about ships?
The horizon effect, yeah.
Yeah.
Anyone who's been to the ocean has seen this. When you watch a ship sail away from you, it doesn't just get smaller and smaller until it's a dot.
No, the hull disappears first.
The hull goes first, then the mast sinks down, and the very last thing you see is the tip of the sail before it's gone. It looks exactly like the ship is going over the crest of a hill.
Because it is. It's going over the hill of the Earth's curvature. So Aristotle gets the shape right. He's got the sphere, but he gets the position completely wrong.
Drastically wrong. Aristotle was convinced the Earth was stationary. He thought we were the dead center of the entire universe. For him, the sun, the moon, the planets, the stars, everything moved in perfect circles around us.
Why circles? Was there any data for that, or was it just a feeling?
It wasn't really data-driven. It was more mystical. For the Greeks, the circle was the most perfect shape, no beginning, no end. And since the heavens were supposed to be the realm of the gods, divine and perfect, they had to move the most perfect way possible. So circular motion wasn't a hypothesis to be tested. It was a philosophical necessity.
Which then brings us to Ptolemy in the 2nd century AD. He takes Aristotle's basic idea and tries to build a full-blown, working cosmological model out of it.
Yes, the Ptolemaic system. And this became the standard map of the cosmos for, over 1,000 years? You have to imagine the Earth sitting in the center, and it's surrounded by these 8 nested crystalline spheres, like transparent layers of an onion.
And each sphere is carrying one of the celestial bodies.
Right. The innermost sphere carried the moon. Yeah. Then you had Mercury, Venus, the Sun, Mars, Jupiter, Saturn. And then the final outermost sphere carried all the fixed stars, the ones that make up the constellations.
It sounds very elegant, the giant cosmic clockwork.
It was elegant, but it had a really dirty secret. It didn't actually work that well. When astronomers tried to use it to predict exactly where, say, Mars or Venus would be in the sky next month, the simple circular orbits just didn't fit what they saw.
So what did Ptolemy do? Did he ditch the circles?
No, he doubled down on them. He hacked his own model. He added these things called epicycles, which were little circles on top of the big circles. And to make the moon's motion fit the data, he had to assume that the moon followed this weird path that sometimes brought it twice as close to the Earth as at other times.
Wait, hold on a second. If the moon gets twice as close to us, shouldn't it look twice as big in the sky?
It absolutely should. And Ptolemy knew that. It was a massive glaring flaw in his own model. But the system was so useful for making, good enough predictions that people just sort of agreed to ignore the fact that the moon never actually ballooned to giant proportions.
That's amazing. We just chose to ignore the evidence of our own eyes because the model was convenient.
And it was comfortable. The church, in particular, really adopted this model because it worked theologically. It left all this room outside that final sphere of fixed stars for heaven and hell. It kept the universe finite, ordered, and most importantly, centered on humanity.
So we have this model that works, kind of, and it keeps everyone happy. It took a really long time to break that. We have to jump forward all the way to 1514.
And we meet Nicholas Copernicus, a Polish priest of all things.
Yeah.
He's the one who proposes a heliocentric model sun at the center, with the Earth orbiting it. But he was so terrified of being branded a heretic that he only circulated his ideas anonymously at first.
Which you can understand. I mean, moving the Earth from the center of everything, That's a huge demotion for humanity. It's basically saying we're not the main character of the universe.
Exactly. And to be fair, Copernicus's model, it wasn't actually that much better at predicting planetary positions than Ptolemy's, because Copernicus was still stuck on using perfect circles. The real death blow to the old Aristotelian view didn't come until 1609.
And this is one of my favorite moments in all of science history. Galileo points a telescope at the sky.
And it just changes everything. He starts looking around with this new invention. And when he points it at Jupiter, he sees these 4 little dots of light near it. He keeps watching them night after night, and he realizes they aren't stars. They're moving. They're orbiting Jupiter.
And that breaks the fundamental rule.
It shatters it. The Ptolemaic rule was that everything orbits the Earth. And here, Galileo had visible proof of 4 moons orbiting something else entirely. If moons can orbit Jupiter, then the Earth doesn't have to be the center of everything.
At the same time this is happening, you have Johannes Kepler working on the math, on the theoretical side. And he finally figures out the missing piece of the puzzle about the shape of the orbits.
Kepler is such a fascinating character because he wanted the orbits to be circles, just as much as Aristotle did. He tried for years just grinding away at the data, trying to make it fit circles. But in the end, he had to give up and just bow to the facts. The planets move in ellipses, these kind of squashed circles.
But he wasn't happy about it, was he?
He hated it. He called ellipses imperfect and repulsive. It was like finding a big scratch on a perfect piece of art. He accepted it because it finally made the predictions match the observations perfectly. But he couldn't explain why. Why would nature choose such an ugly shape?
He had some ideas about it being magnetic forces from the sun or something.
Right. He was missing the engine. He had the map of the solar system, but he didn't know what was making the car go. That engine wouldn't be discovered until 1687.
And here is where things get really, really interesting. Isaac Newton.
Philosophiae Naturalis Principia Mathematica. I mean, you could argue it's the single most important scientific book ever written. Newton didn't just describe how things moved. He invented the mathematics calculus to predict their motion with incredible precision.
And he gave us the concept of gravity.
The law of universal gravitation. It was just a staggering intellectual leap. Newton's big idea was that the force that makes an apple fall from a tree to the ground is the exact same force that keeps the moon flying in its orbit around the Earth.
Which sounds obvious to us now, but back then people thought the heavens operated under a completely different set of rules from Earth.
Totally separate. Newton unified them. He said that every object in the universe attracts every other object. The more massive they are and the closer they are, the stronger that pull. And he proved, mathematically, that this force would cause planets to move in. Ellipses.
So he proved Kepler right. He finally explained the why.
He did. But in solving that problem, the problem of planetary motion, Newton stumbled into a brand new, even bigger paradox. A paradox about the nature of the entire universe.
This is the static universe problem.
That's it. If gravity is always attractive, if every star is pulling on every other star, why doesn't the whole universe just crunch together? Why hasn't it all collapsed into one giant ball?
That's a great question. If I just toss a bunch of magnets into a box, they all clump up.
Newton was really troubled by this. He knew the universe wasn't collapsing because, well, here we are. So to solve it, he came up with a clever but ultimately flawed argument. He relied on the idea of infinity.
How does infinity fix the gravity problem?
He argued that if the universe is infinite and it contains an infinite number of stars that are spread out more or less evenly, then there is no center to fall toward.
Oh, I see. So if I'm a star, I'm getting pulled to the left, but I'm also getting pulled to the right an equal amount. I'm pulled up and I'm pulled down. And if all those pulls are infinite and in every direction, they just cancel each other out.
That was the logic.
Yeah.
It's a very delicate balancing act. But we now know the kind of equilibrium is fundamentally unstable. It's like trying to balance a pencil perfectly on its tip. It might stay there for a split second, but the tiniest vibration will make it fall over.
Right.
In an infinite universe, if one region just happens to become a tiny bit denser, its gravity gets stronger and it starts a chain reaction. The collapse begins.
But back then, the idea of an eternal, unchanging, static universe was so powerful that they preferred this precarious, infinite model over the alternative.
Because the only alternative was that the universe was either expanding or contracting, that had a beginning or an end. And that felt, well, it felt too much like theology, not like proper science.
Speaking of problems with an infinite universe, we have to talk about Olber's paradox. This is one of those things that sounds so simple on the surface, but it's actually really profound.
It's the paradox of the dark night sky.
Which at first sounds like a silly question. The sky is dark at night because the sun is on the other side of the planet.
Right, that explains local day and night. But think about Newton's infinite model again. An infinite universe filled with an infinite number of stars. If that's true, then no matter where you look in the sky, no matter what tiny patch you point a telescope at, your line of sight should eventually end on the surface of a star.
It's like being in the middle of a really, really dense forest. Everywhere you look, your view is blocked by a tree trunk. You can't see out of the forest.
Exactly.
Yeah.
So in an infinite static universe, the entire sky should be a solid wall of starlight. The night sky should be as bright as the surface of the sun. We shouldn't even have night.
But obviously we do. The sky is mostly black, so something is deeply wrong with the model.
Heinrich Olbers pointed this out formally in 1823. He tried to solve it by suggesting that maybe distant dust clouds were just blocking the light from the faraway stars.
That sounds plausible. Space is full of dust.
It sounds plausible, but it fails because of thermodynamics. If those dust clouds block the starlight, they absorb all that energy. And eventually, the dust clouds themselves would heat up until they glowed just as brightly as the stars they were blocking. They become light sources themselves.
The dust just becomes another light bulb.
That's it. So if the universe is infinite and has existed forever, the sky must be bright. Since it's dark, one of those assumptions has to be wrong.
The only way out is to assume the scans haven't been shining forever.
Precisely. The light from the most distant stars simply hasn't had time to reach us yet, because they only turned on a finite time ago, which implies the universe itself has a history. It had a beginning.
And this whole idea of a beginning was a huge philosophical battlefield for centuries, right?
Yeah.
You had the religious camp on one side and the scientific camp on the other.
It was very messy. You had figures like St. Augustine arguing for first cause, a moment of divine creation. But then you had Aristotle and the Greeks who really disliked the idea of a beginning. It implied divine intervention, so they much preferred an eternal universe that had just always existed.
And then you get the philosopher Immanuel Kant, who just muddies the waters by trying to argue both sides are right.
He called them his antinomies. He came up with these logical proofs for the thesis, the universe has a beginning, and the antithesis, the universe is eternal. And he argued both were logically sound and also logically flawed.
How could they both be flawed?
Well, his argument against a beginning was, if the universe had a start, why did it wait an infinite amount of time before starting? Why then and not sooner? But his argument against an eternal universe was that it would mean an infinite amount of time has already passed to get to the present moment, which he felt was an impossible task to complete.
It's a total brain twister. It feels like you're getting caught in a language trap.
It really is. And amazingly, St. Augustine had offered a solution centuries earlier that was way ahead of its time. He basically said that time itself is a property of the universe. Time did not exist before the beginning.
So you can't ask what happened before the universe started because the word before has no meaning.
Exactly. Hawking uses a great analogy. It's like asking, what is north of the North Pole? It's not that there's nothing there. It's that the question itself is meaningless. The definition of north ends at the pole. The definition of time ends at the beginning of the universe.
So for hundreds of years, this was all just philosophy, people arguing back and forth. But then, in 1929, the debate moves from the philosophy department to the observatory.
Edwin Hubble. He's at the Mount Wilson Observatory. He's looking at distant galaxies, and he's analyzing the light coming from them.
And he finds the redshift.
The redshift, it's the Doppler effect, but for light. Just like an ambulance siren sounds lower in pitch as it moves away from you, light from an object moving away from you gets stretched out and appears redder. Hubble found that almost every galaxy he looked at was redshifted. They were all moving away from us.
And not just moving away. The farther away they were, the faster they were moving away.
Which is the classic signature of an explosion. The universe is expanding. And if you run that movie backwards, everything gets closer and closer and closer together until you reach a point in the finite past where everything is in the same place.
The Big Bang.
The Big Bang, a moment of infinite density, a singularity. And that discovery, that single observation, took the concept of a beginning out of the hands of the philosophers and put it squarely into the realm of physics.
So, wow. We've gone from turtles to spheres to ellipses to gravity to an expanding universe. We've completely changed our picture of what the universe is. But to really understand Hawking's work, we now have to change our understanding of the stage everything is happening on. We have to dive into Chapter 2, Space and Time.
And this is where things get really counterintuitive. Because for almost all of human history, we just assumed space and time were the background. just the empty, passive container that all the events of the universe happened inside.
And to see why that's wrong, we actually have to go back and revisit our old friends Aristotle and Galileo, but this time talking about motion.
Right, so Aristotle had this very intuitive idea that the natural state of any object is to be at rest. If you push a cart, it moves. When you stop pushing, it stops. So for him, rest was the default state, and you needed a constant force to maintain motion.
Which makes total sense in our everyday lives. If I stop pedaling my bike, I slow down and stop.
But Galileo realized that our daily experience is completely dominated by a hidden force: friction. He argued that if you could get rid of all friction, if you had a perfectly smooth surface in a vacuum, an object in motion would just keep moving in a straight line forever.
He also completely demolished Aristotle's idea about falling objects, the idea that heavy things fall faster because they have a stronger desire to get back to the earth.
Exactly. The legend is that he dropped cannonballs from the Leaning Tower of Pisa. Historians doubt that actually happened, but he definitely did experiments rolling balls down very smooth, inclined planes. And he found that weight makes no difference.
So a feather and a lead ball fall at the exact same rate as long as there's no air resistance.
Precisely. In a vacuum, they hit the ground at the same time. One of the Apollo astronauts famously did this on the moon with a hammer and a feather to prove the point live on television.
So force doesn't just create motion, force changes motion. It creates acceleration.
And this is the foundation of Newton's laws. A body will stay at rest or keep moving in a straight line at a constant speed unless a force acts on it. And this implies something radical. There is no absolute state of rest.
This is the famous train example, right?
The train example. Imagine you're on a perfectly smooth train moving at a constant 100 miles per hour. The windows are all blacked out. If you put a ping pong ball on the table in front of you, it just stays there. If you drop it, it falls straight down to your feet.
There is no experiment I can do inside that train to prove that I'm moving.
None whatsoever. From your perspective, you could say the train is moving at 100 miles per hour and the ground is stationary. Or you could just as validly say the train is stationary and the ground is moving backwards at 100 miles per hour. The laws of physics work identically in both cases. This abolished the idea of absolute space.
But, and this is the huge but, Newton still held on to one absolute.
Absolute time. Newton was convinced that time was universal and completely separate from space. He believed in a master clock for the universe. If a second ticked by for me on the train, 1 second also ticked by for you on the ground, period.
And that seems just completely obvious. Why would my speed affect my watch?
It seems obvious because we live our lives at very, very slow speeds. But the whole idea completely falls apart once you start dealing with the speed of light.
Okay, so let's talk about light. For a long time, people just assumed light was instantaneous. You light a candle, and the whole room is lit up immediately.
Until an astronomer named Ole Romer in 1676, he, again, studying the moons of Jupiter, and he noticed a funny pattern. The eclipses of Jupiter's moons, when they pass behind the planet, seemed to happen a few minutes late when the Earth was on the far side of the sun from Jupiter, and they happened early when we were on the near side.
Because the light from the eclipse had to travel that extra distance across Earth's orbit to reach his telescope.
Exactly. He realized light must have a finite speed. His calculation was around 140,000 miles per second. The modern value is 186,000, so he was in the ballpark. But the key thing is he proved light wasn't instant.
Then we fast forward to James Clerk Maxwell in 1865. He unifies the theories of electricity and magnetism. And his equations predict that electromagnetic waves, radio, light, X-rays should all travel at a very specific, fixed speed.
And this created a massive, massive conflict with Newton's laws of motion.
Why?
Because of the train again. Newtonian physicists' speeds add up. If I'm on a train going 100 miles per hour and I throw a ball forward at 10 miles per hour, its speed relative to the ground is 110 miles per hour.
Right. Simple addition.
So what happens if I stand on the train and I shine a flashlight forward? According to Newton, that beam of light should be moving at the speed of light plus 100 miles per hour. But Maxwell's equation said the speed of light is a constant. It's always the same number.
So Newton says yes, Maxwell says no.
That was the crisis. And scientists tried to solve it by inventing a substance called the ether. They imagined that all of space was filled with this invisible, undetectable substance, and light was a wave traveling through the ether. So the speed of light was fixed, but it was fixed relative to the ether.
So if the Earth is moving through this ether, we should feel an ether wind, right? Like when you stick your hand out of a moving car window.
Exactly. And in 1887, two American physicists, Michelson and Morley, built an incredibly sensitive experiment to detect this ether wind. They measured the speed of light in the direction of Earth's orbit and also perpendicular to it. They fully expected to see a slight difference caused by the drag.
And what did they find?
Nothing. Zero. The speed of light was exactly the same in all directions, no matter how the Earth was moving. The eco wind didn't exist. The
Yeah.
ether didn't exist.
So now physics is completely broken. You have this undeniable experimental fact. The speed of light is the same for every single observer, no matter how fast they are moving.
Enter Albert Einstein, 1905, his special theory of relativity.
And he basically looked at the wreckage of the ether theory and just said, okay, let's not fight the result. Let's just accept it as a fundamental principle.
He built his whole theory on two postulates. One, the laws of science are the same for all freely moving observers.
Yeah.
Two, the speed of light is the same for all observers.
But that creates a huge logical problem because speed is just distance divided by time, s equals d over t.
Right.
So if I'm on a spaceship flying past you at half the speed of light and I shine a laser forward, I measure that beam moving away from my ship at the speed of light. You, standing still on an asteroid, also measure that same beam moving at the speed of light.
Correct. We both agree on the speed, the s, in the equation, but clearly we disagree on the distance, the d, that the light has traveled relative to each of us.
So if we agree on speed but we disagree on distance, the math demands that we must also disagree on time.
That's it. That's the leap. For the equation SDT to hold true for both of us, the t variable, time itself, has to change. My second and your second are not the same duration.
And that is the death of absolute time.
It's gone. Time is relative. It depends on your motion. The faster you move through space, the slower you move through time, relative to a stationary observer.
Hawking uses this to explain the concept of the light cone, which is a way of visualizing cause and effect.
Right, because if nothing can travel faster than light, it means there's a built-in delay in the universe. An event can't affect you until the light from that event reaches you.
He uses the example of the sun just going out.
Yeah. If the sun were to suddenly cease to exist, right now, this very second, we wouldn't know. For 8 minutes, we would still see it shining. We'd still feel its heat. Life would go on as normal.
Because the light and the gravity takes 8 minutes to travel from the sun to the Earth.
Right, so the event the sun vanishes happened. But for us, it's not in our past light cone yet. It's in a region of space-time called the elsewhere. We are causally disconnected from it. Only after 8 minutes does that event enter our past, and we experience the consequences.
So there's no such thing as a universal now that applies to the whole galaxy.
None. But special relativity, as amazing as it was, had a huge hole in it. It worked beautifully for electromagnetism and motion, but it was completely incompatible with gravity.
Why not?
Because Newton's theory of gravity was instantaneous. In Newton's model, if the sun vanished, the Earth would instantly fly off its orbit. But Einstein's theory said nothing, not even gravity, can travel faster than light.
So Einstein spends the next 10 years just banging his head against this problem.
And in 1915, he publishes the general theory of relativity, and this is his masterpiece.
So how did he finally square gravity with the speed of light?
He did it by getting rid of gravity as a force altogether. He had this revolutionary idea that gravity isn't some invisible rope pulling things together. He said gravity is what you feel when you move through curved spacetime.
The curvature of space-time?
Yes. He proposed that massive objects like the sun don't create a force field. Instead, they literally warp and bend the fabric of space and time around them.
This is the classic bowling ball on a trampoline analogy. You put a heavy ball in the middle and the rubber sheet sags down. Then if you roll a little marble nearby, it orbits the bowling ball. Not because the ball is pulling it, but because the surface it's rolling on is curved.
That's the perfect analogy for space. And Hawking adds another one for time. Imagine an airplane flying in a perfectly straight line over hilly terrain. The plane itself is flying straight. That's called geodesic. But if you watch its shadow on the ground, the shadow goes up and down over the hills. The shadow's path looks curved.
So the Earth isn't being pulled by the sun. The Earth is just trying to move in a straight line through space-time.
Exactly. But the sun's massive presence has curved the spacetime around it so much that our straight-line path ends up being bent into what we perceive as an elliptical orbit. Gravity isn't a force, it's geometry.
This sounds like something out of science fiction. How could he possibly prove it?
He proposed 3 key tests. The first was the orbit of Mercury. For decades, astronomers had known that Mercury's orbit wobbles in a way that Newton's laws just couldn't fully explain. Einstein's equations for curved spacetime predicted the wobble perfectly.
Okay, that's one. What was the second?
The bending of starlight. If massive objects curve space, then light shouldn't travel in a perfectly straight line when it passes near one. It should follow the curve.
So you should be able to see a star that's technically hidden behind the sun because its light would bend around the sun to reach our eyes?
Precisely. In 1919, a British expedition led by Sir Arthur Eddington traveled to West Africa to observe a total solar eclipse. During the eclipse, they took photographs of the stars right next to the sun's edge, and they found that the stars' positions had shifted. The sun's gravity had bent their light.
But Hawking adds a funny little footnote to that story.
He does. He points out that, in hindsight, the 1919 measurements were actually pretty sloppy. The experimental errors were about as large as the effect they were trying to measure. They basically got lucky and found the result they were looking for. It wasn't until much later that the effect was confirmed with high precision. But at the time, the headlines made Einstein an international celebrity overnight.
And the third proof, this one brings us back to time. Time dilation from gravity.
General relativity predicts that time itself runs slower in stronger gravitational fields. A clock closer to a massive body will kick slower than a clock farther away.
So technically, my feet are aging a tiny bit slower than my head.
By an infinitesimally small fraction, yes. But it's real, and it's measurable. In 1962, they put hyper-accurate atomic clocks at the bottom and top of a water tower. And sure enough, the clock at the bottom ran measurably slower.
And this isn't just some weird theoretical quirk. It matters for our everyday lives.
It's absolutely vital. The GPS system in your car or your phone relies on signals from satellites orbiting the Earth. Those satellites are in a weaker gravitational field than we are, so their clocks run faster. If the engineers didn't use Einstein's equations to constantly correct for that time difference, your GPS position would drift by about 6 or 7 miles every single day. The whole system would be useless.
That is just... it's mind-blowing. Google Maps works because of curved space-time.
It is a direct, practical application, and all of this leads to the famous twins paradox.
Okay, walk us through that one.
So you have a pair of twins. One stays on Earth. The other gets into a super-fast spaceship, travels to a distant star, and then comes back.
In Newton's world, with absolute time, they'd come back and be the same age.
Right. But in Einstein's world, the traveling twin has experienced both high-speed motion and different gravitational fields. Both of those things slow down time. So when he returns, he might have aged only 5 years, while his twin brother back on Earth has aged 50 years.
And it's not an illusion. He is biologically, physically younger.
He is. It's only a paradox if you're still clinging to the idea of absolute time. In reality, everyone carries their own personal clock, and its speed depends on how you move through space-time.
Which brings us to the grand conclusion of these first 2 chapters, this huge paradigm shift, the move from a static universe to a dynamic one.
This is the absolute key takeaway. Before 1915, space and time were seen as a fixed, absolute, passive arena, a stage. The actors, the stars and planets, moved around on the stage, but the stage itself never changed.
But Einstein showed that the stage is part of the show.
The stage is an active participant in the play. Space and time are warped and stretched by the actors. And here's the crucial part. If space-time is dynamic, if it can bend and stretch, it doesn't have to be static. It can expand. It can contract. It can have a beginning and it can have an end.
General relativity killed the idea of an eternal, unchanging universe. It practically forces you to confront the Big Bang.
And that's exactly where we have to go next. We've laid the groundwork. We've seen how we got this new dynamic picture of the universe.
We have gone from turtles all the way to curved space-time. We've learned that time is relative, gravity is just geometry, and that the universe almost certainly had a beginning.
And we are really just getting started, because the classical theory of gravity, general relativity, is beautiful, but it predicts its own downfall. It predicts points where it breaks down. It predicts singularities, black holes, the beginning of time itself.
In the next part, we will discuss the expanding universe and the fundamental uncertainty that governs our reality through the expanding universe and the uncertainty principle.
We're going to see what happens when the very, very big world of Einstein crashes into the very, very small world of quantum mechanics.
I cannot wait. But for now, here's a thought to leave you with. If your personal time depends on your speed and the gravity you feel, are you really living in the same now as the person sitting next to you? Or is your moment in time, in some profound way, entirely your own?
Thanks for listening to Fact Horizon. We'll see you in the next deep dive.
Keep looking up. Welcome back to the deep dive. We are continuing our journey through one of the most significant scientific books ever written, Stephen Hawking's A Brief History of Time.
Hmm.
If you were with us for part one, we tackled the heavy hitters, gravity, and the nature of time itself. But today we are going much, much bigger.
And at the same time, much, much smaller.
Yeah, it's a real study in contrast.
It is. We're moving from the scale of the entire cosmos
Yeah.
all the way down to the subatomic world. And what we're finding is that our intuition, it just fails us in both places.
Okay, so just to set the roadmap for everyone listening, this is part two where we explore chapters, the expanding universe, and the uncertainty principle.
Welcome to Fact Horizon. This is where history meets mystery and facts to find the future.
Let's set the stage properly then. In our last conversation, we talked about how we used to view time as this absolute straight line. But there was another assumption people had for centuries, right?
Oh, absolutely.
That the universe was just there, like a static stage that never changes.
The static universe. It's actually quite an intuitive idea. I mean, you look up at the night sky, and apart from the planets moving around, the stars seem fixed. They seem eternal.
Right.
And until the early 20th century, the prevailing scientific consensus, even held by brilliant minds like Albert Einstein, was that the universe was eternal, unchanging, and static. It had always existed, and it always would, in more or less the same state.
It sounds kind of comforting. Stable.
It is comforting. But as we're about to find out, that stability was, well, it was an illusion. We're going to look at two discoveries that basically broke physics. One showed us the universe is exploding outward, and the other showed us that at the smallest scales, reality is basically just rolling the dice.
It really is a shift in perspective. We go from a predictable, almost clockwork universe to one that is expanding into the unknown and just vibrating with uncertainty.
Yep. Let's start with the big stuff.
Let's unpack the expansion first. This brings us to a name everyone knows because of the Space Telescope, Edwin Hubble. But before we get to what he found in 1924, I have to ask a really basic question. How do we even know how far away things are? I mean, we can't exactly stretch a tape measure to the stars.
No, you can't. And that was the big hurdle for centuries. For nearby stars, astronomers use something called parallax. It's just simple geometry, really.
Parallax, okay.
As Earth orbits the sun, our position changes. So the apparent position of a nearby star shifts slightly against the background of much farther stars.
Oh, wait. So is that kind of like, if you hold your finger up in front of you
Mm-hmm.
and you close one eye and then the other, and your finger seems to jump back and forth against the wall?
That is it. That's the exact same principle. Your eyes are just at different points in Earth's orbit. But here's the problem. That finger trick only works for your close neighbors. For the truly vast, crushing distances of deep space, that shift is just too tiny to measure.
Okay. So it's useless for really distant stuff.
Right. So Hubble had to use a different method. He used luminosity or brightness.
But wait, isn't that risky? I mean, a bright light really far away looks the same as a dim light that's close up. How do you know which is which?
You've hit on the exact problem. You need a reference point. Hubble needed what we call a standard candle.
Oh,
And he found one in a specific type of star, a Cepheid variable, where we know exactly how bright it should be based on how it pulses.
okay. So if you know it's supposed to be a 100-watt bulb, but it looks like a 5-watt bulb, you can do the math and figure out the distance.
Precisely. And when Hubble started finding these stars in these faint, fuzzy patches of light that people just thought were gas clouds nearby.
Right, nebulae.
Exactly. He calculated their distances and realized something absolutely shocking. They were way too far away to be part of the Milky Way. They were entirely separate galaxies,
That is the moment the universe just got instantly bitter.
exponentially bigger. I mean, all of a sudden, the Milky Way wasn't the universe. It was just one of hundreds of thousands of millions of galaxies separated by these vast, vast tracts of empty space.
Okay, so the universe is huge. I get that. But that doesn't prove it's moving.
Right.
Where does the expansion come in?
That comes from analyzing the light itself. This is the smoking gun. When you pass light through a prism, it splits into a spectrum. Colors like a rainbow. But if a star or a galaxy is moving, that spectrum shifts.
Moves how? Like the colors actually change.
Think about sound for a second. Have you ever stood on a sidewalk when an ambulance drives by with its siren on?
Sure, it goes meow. The pitch gets higher coming at you and lower going away.
That's the Doppler effect. Sound is a wave. When the ambulance rushes towards you, it squashes the waves together. That's a higher pitch. When it runs away from you, the waves stretch out a lower pitch.
Okay, I'm with you.
Light behaves in the exact same way.
So if a galaxy is moving toward us, the light waves get squashed.
Yes, and that shifts them toward the blue end of the spectrum. But if it's moving away, the waves stretch out toward the red end. We call that redshift.
So Hubble starts looking at all these galaxies. I'm guessing he expected random movement. Some coming at us, some going away, a chaotic swarm.
That's exactly what he expected, a static, chaotic universe. But in 1929, he published what we now call Hubble's law. He found that nearly all galaxies are redshifted.
So everything is moving away from us.
Everything. And here is the real kicker. The farther away a galaxy is, the faster it is moving.
That feels really significant. It's not just shrapnel from an explosion flying at different speeds. The speed is directly related to the distance.
It means the space between the galaxies is stretching.
Yeah.
And this just destroys the idea of a static universe. If everything is moving apart, then the universe is expanding.
And this brings us to what Hawking calls Einstein's blunder, because ironically, Newton's theory of gravity actually should have predicted this, shouldn't it? Gravity pulls things together. A static universe shouldn't stay static.
It really shouldn't. Gravity is attractive. If the universe were just sitting there, static, gravity should eventually pull all the stars into one giant pile. It should collapse.
So why didn't Einstein see it? He had the general theory of relativity. He had the tools.
He had the math, but he also had, well, human bias. Einstein was so philosophically committed to the idea of an eternal, unchanging universe that he just couldn't accept what his own equations were telling him.
So he changed them.
He did. He actually modified his theory. He added something called the cosmological constant, which is essentially a made-up anti-gravity force, just to balance out the attraction of gravity and keep the universe steady.
He fudged the numbers to match his worldview.
Pretty much. And later, after Hubble's discovery, he called it the greatest mistake of his life. But what's really interesting is that a Russian physicist, a guy named Alexander Friedman, he didn't have that bias.
Okay.
Years before Hubble, Friedman just took Einstein's equations and assumed the universe looks the same in every direction. And the math told him the universe had to be moving.
He trusted the math more than the dogma.
And he was right.
So if everything is moving away from us, it really feels like we must be special, like we're the center of the explosion. But Friedman's model says that's not the case.
It's a very common misconception. But think about it like this. Imagine a balloon with spots painted all over it. As you blow up the balloon, every spot moves away from every other spot.
Okay, I can see that.
Now, if you were a tiny bug standing on one of those spots, you'd see all the other spots rushing away from you. But are you at the center?
No, there's no center on the surface of the balloon.
Exactly. Every point experiences the same expansion. The universe doesn't have a center. Space itself is the rubber of the balloon that's stretching.
That really helps visualize it. But this leads to a pretty heavy realization. If everything is moving apart now, that means yesterday it was all closer. And 1 billion years ago, even closer still.
If you rewind the cosmic movie, you eventually get to a point somewhere between 10 and 20 billion years ago where the distance between all galaxies was zero.
Zero. Like everything was touching.
Closer than touching. It was a point of infinite density, infinite curvature of space-time. This is what we call the Big Bang singularity.
And this is where the laws of physics just, what? Do they just break down?
They fail completely. General relativity actually predicts its own downfall here. You can't use science to predict what happened before this point because time itself, as we define it, it starts at the Big Bang.
So asking what happened before the Big Bang is?
As Hawking puts it, it's like asking what is north of the North Pole. The question doesn't have a definition in our system. The concept of before doesn't even exist yet.
That is genuinely mind-bending. It's a hard wall for knowledge. But let's look the other way. If the universe started with this bang and is expanding, where is it going? What's the fate of the universe?
This is where Friedman's work gets really fascinating and a little bleak, to be honest. He proposed 3 mathematical models, 3 possible fates depending on this cosmic tug-of-war between the momentum of expansion and the pull of gravity.
Okay, so who wins?
Well, scenario 1 is the big crunch. In this model, gravity is strong enough to win the war. The expansion slows down, it stops, and then it reverses. The whole universe collapses back into a singularity.
So the movie just plays in reverse.
Exactly. In this model, space is curved like a sphere. It's finite, but it has no boundary. Sort of like the surface of the Earth. If you traveled in a straight line long enough in this universe, you'd eventually come back to where you started.
Wow. Okay, that's a bit claustrophobic. What's scenario 2?
That's the open universe. In this one, the expansion is so fast that gravity loses. decisively. The galaxies just fly apart forever and ever. Here, space is curved like a saddle. It bends up in one direction and down in another. It's infinite.
And what does that look like billions and billions of years from now?
Cold and dark. The stars burn out, the galaxies drift so far apart they can't see each other anymore. It's what they call the heat death of the universe.
Well, that's cheerful. Is there a middle ground? A happier ending?
There is the flat universe. This is the Goldilocks scenario. The expansion is just fast enough to avoid collapse, but it slows down over an infinite amount of time. The speed approaches zero, but never quite gets there.
And in that one, space is just flat.
Right. Parallel lines stay parallel forever.
So which one are we in? Do we know? Are we going to crunch, or are we going to drift apart forever?
It all depends on density. How much stuff is in the universe to generate enough gravity to pull it all back?
And we can see the stars, we can count the galaxies. Is that enough to crunch us?
Not even close.
Yeah.
If we only count what we can see, the visible matter, then the answer is a definite no. We'd fly apart forever. But we know there is more out there. We see galaxies spinning so fast they should rip themselves apart if they only contained the stars we see.
Right. Dark matter.
Exactly. There has to be this unseen matter holding them together with its gravity. But even when we estimate all that dark matter, we still only come up with about 1/10 of the mass needed to stop the expansion.
So the current verdict is?
The current verdict is, unless we are missing something absolutely massive, the evidence suggests we will likely expand forever. A cold, lonely drift into the dark.
I feel like we need a break after that. It really shows how far we've come from thinking the universe was just this static, safe, eternal box.
It totally changes our place in things. But hold on, because if you think the expanding universe shattered our sense of stability, wait until we look at the microscopic world.
Right.
Because at the exact same time astronomers were looking out and destroying the idea of a static stage, physicists were looking in and destroying the idea of the predictable actor.
This is the bridge, then. Both of these discoveries were attacking the same old idea, determinism.
The dream of the Marquis de Laplace. Back in the early 19th century, he suggested that the universe was basically a giant machine. If we could just know the position and the speed of every single particle in the universe at one moment,
We could calculate the entire future.
and the entire past. It's a comforting thought. It means everything. The weather, the stock market, me dropping my coffee this morning, it's all predetermined. If you have enough data, you can predict everything.
But in the 1920s, a guy named Werner Heisenberg comes along and proves that this dream wasn't just difficult, it was fundamentally impossible.
This is the uncertainty principle.
Yeah.
And I think a lot of people misunderstand this. They think it just means, oh, our equipment isn't good enough yet.
Right, that we just need better tools.
But it has nothing to do with bad microscopes. It has to do with the very nature of observation itself. Imagine you want to measure the position of a particle, say an electron, and its speed at the same time.
Okay, so I need to look at it somehow.
And to look at it, you have to shine light on it. But as Max Planck had discovered, light isn't a continuous stream. It comes in these little discrete packets like tiny bullets of energy called quanta.
So I'm literally shooting bullets of light at this tiny electron.
You are. And when that packet of light, that quantum, hits the electron to measure it, the energy from the light gives the electron a kick. It changes its velocity.
Oh, so by checking where it is, I've just changed how fast it's going.
Exactly. And here's the trap. If you want to know the position very, very precisely, you need to use light with a very short wavelength. But short wavelengths have high energy.
So the harder I look at the position, the harder I kick it, and the less I know about the speed.
And if you use gentle, low-energy light to not disturb the speed, the waves are too long and floppy to give you a precise position. You can know one or you can know the other. But nature physically forbids you from knowing both simultaneously with perfect precision.
That is deeply frustrating. So Laplace's dream is dead. We literally cannot predict the future because we can't even measure the present without messing it up.
Determinism is gone. We had to accept that at the fundamental level, the universe is not clockwork. It is governed by chance and probability.
Which leads us into the weirdest part of the book for me, chapter 4, and this idea of wave-particle duality. Because if we can't pin down a particle, then what even is it? Just a smear of probability.
It birthed quantum mechanics. We stopped talking about definite paths and started talking about quantum states. And this revealed that matter has a sort of split personality. We used to think light was a wave and electrons were hard little particles.
Little tiny marbles.
Right. But quantum mechanics showed us that light can behave like a particle, and electrons matter can behave like
An
waves.
electron, a piece of solid matter, behaving like a ripple on a pond. My brain just does not want to accept that.
It doesn't make intuitive sense, no. But we see it in experiments with something called interference. If you have two waves on a pond and the crest of one meets the trough of another, they cancel each other out. Electrons do
They
this.
interfere with each other.
And remarkably, this wave behavior is the reason you and I are sitting here and not collapsing into a pile of goo.
Okay, walk me through that. How does an electron being a wave save the atom from collapsing?
In classical physics, an electron orbiting a nucleus is like a tiny planet orbiting a sun. But an electron is charged. As it spins, it should radiate energy. It should lose speed, spiral inward, and just crash into the nucleus. All matter should collapse instantly.
But it doesn't, obviously.
It doesn't, because of the wave nature. Think of a guitar string. When you pluck it, it vibrates, but it only vibrates at certain frequencies, specific notes where the wave fits perfectly along the length of the string. You can't play a note between the harmonics.
Right. The wave has to fit. It has to resonate.
Niels Bohr realized the electron is the same. It can only exist in orbits where its wave reinforces itself, where a whole number of wavelengths fit perfectly around the circle. The orbits in between, where the waves would cancel themselves out, they simply don't exist. They're forbidden.
So the electron can't spiral in because there's no string for it to vibrate on between the allowed orbits.
Exactly. Quantum mechanics saves the atom by forcing the electron to stay in these discrete, safe energy levels.
That is wild. The fundamental uncertainty is actually what gives matter its structure. But Hawking takes this even further with a concept from Richard Feynman. And honestly, this is the part where my brain started to hurt. The sum over histories.
It is a beautiful and bizarre concept. In the old way of thinking, a particle goes from point A to point B along one specific path, a straight line or an arc.
Right. I throw a ball to you, it flies through the air in a simple arc.
Feynman said no. In quantum mechanics, a particle doesn't take one path. It takes every single possible path simultaneously.
Wait, you need to define every possible path.
I mean, every path. In the quantum view, the particle travels in a straight line, yes. But it also travels in a loop. It also travels to the Andromeda galaxy, stops for a quick coffee, does a dance on a supernova, and then comes back to hit the target.
That sounds completely absurd. We don't see baseballs visiting Andromeda during a game?
We don't. And that's because of interference. For all those crazy, long, winding paths like that trip to Andromeda, the waves associated with them are out of phase with the waves of their neighboring paths. They cancel each other out.
So the crazy history is just, they destroy each other through interference.
Yes. But the paths that make sense, the ones that are close to the classical straight line, their waves are all in sync and they reinforce each other. So the reality we see, the ball flying through the air, is just the result of all these infinite possibilities canceling out the weird stuff and leaving behind the probable stuff.
So reality is just the average of infinite madness.
That's a great way to put it, yes.
Wow. So let's try to tie this together. We've gone from Hubble showing us a universe that is exploding outward from a singularity to Heisenberg showing us a microscopic universe that is fundamentally, inescapably uncertain.
It's the two great pillars of modern physics. We have general relativity, which is beautiful and elegant at describing gravity and the expanding universe, the very large. And then we have quantum mechanics, which handles the uncertainty and probabilities of the atom, the very small.
But the book hints at a pretty major problem. They don't get along, do they?
They hate each other. They're mathematically inconsistent. Relativity requires smooth, predictable curves in spacetime. Quantum mechanics is jagged, uncertain, and jittery.
And usually that's fine, right? Because stars are big and atoms are small, so you just use the right tool for the job.
Usually. But what about the Big Bang? Or deep inside a black hole? You have a situation where the universe was incredibly massive and infinitesimally small at the same time. Both theories have to apply.
And they just crash.
They break.
Right.
That's the holy grail Hawking is chasing. The unified theory. The theory of everything.
A single theory that works for both.
That is the ultimate goal. To find one set of laws that covers the expanding cosmos and the dancing electron. We aren't there yet, but understanding these two pieces, expansion and uncertainty, is the necessary first step on that journey.
Well, we are going to keep following that path. In the next part, we will delve into the building blocks of nature and the mysterious gravity of space and elementary particles and the forces of nature and black holes.
It only gets stranger from here, believe me.
It certainly does. Thank you for listening and for letting us borrow your time to explore the universe.
Until next time. Today, We're going to the absolute extremes. We're starting with the smallest things in existence, these elementary particles, and then we're zooming out to the most massive, dense objects known to physics, black holes.
It does seem like a strange pairing at first glance, doesn't it? Jumping from the subatomic to the galactic. But
Hmm.
the fascinating thing about Stephen Hawking's work in A Brief History of Time is that he shows us you actually can't understand one without the other.
Really?
Yeah. To understand how a massive star dies and becomes a black hole, you have to understand the tiny rules that govern the particles inside it.
So the very small explains the very huge.
Precisely. It's all connected.
Okay, let's unpack this. We're starting with Chapter 5, Elementary Particles and the Forces of Nature. And I think we have to start with the history of stuff. Like, what is the universe actually made of?
Right.
Because for a long time, we thought it was just earth, air, fire, and water, right? Thanks, Aristotle.
Right. Aristotle's view was that matter was continuous. You could just keep cutting a piece of matter into smaller and smaller chunks forever. No limits.
Just keep dividing.
But there's another Greek, Democritus, who argued that, well, eventually you'd hit a grain you couldn't cut. He called it an atom.
Which means indivisible.
Literally indivisible in Greek. And he was much closer to the truth. But it took a while to prove.
And turns out Democritus was onto something. I was surprised to see Einstein pops up here again. I always associate him with relativity, but he helps prove atoms exist.
He did. In 1905, just weeks before his famous relativity paper, Einstein wrote a paper on something called Brownian motion.
That's the jittery dust in water, right?
Exactly. If you look at dust particles suspended in a liquid, they just style it. They jitter around randomly. Einstein showed this was because invisible atoms in the liquid were colliding with the dust. It was the smoking gun. It proved atoms were real.
But then, of course, the plot twist. We found out the atom isn't actually indivisible. We smashed it open.
We did. We found the electron, thanks to J.J. Thomson. Then Rutherford found this dense little thing at the center, the nucleus, and then Chadwick found the neutron. We realized the atom is mostly empty space with these little particles buzzing around.
But we didn't stop there. And this is where it gets really interesting and honestly a little weird. We found out that protons and neutrons, the heavy parts of the atom, are made of even smaller things.
Quarks.
Quarks.
Murray Gell-Mann named them in 1969, and this is where physicists start having, a bit too much fun with the naming conventions.
Oh, absolutely. I love this. So quarks come in 6 flavors: up, down, strange, charmed, bottom, and top.
And just to be clear to anyone listening, a strange quark isn't actually strange in personality, and a charmed quark isn't, polite.
This is not carrying your groceries for you.
Exactly. These are just labels to distinguish their mass and how they interact with everything else.
And they have colors too, right? Red, green, and blue.
Again, just labels. Quarks are smaller than the wavelength of visible light. They can't possibly have a color we could see. Physicists use color to describe a property they have that acts a bit like electric charge.
So it's an analogy?
It's an analogy, and the rule is you can't have a quark on its own. They always group together in ways that the colors cancel out to white. A proton, for example, is one of each color: a red, a green, a blue quark.
So it's like a subatomic recipe.
Mm-hmm.
But there's another property particles have that Hawking spends a lot of time on, and it seems crucial for, well, everything. Spin.
Spin is fundamental, and it's another one of those quantum ideas that's hard to visualize. You can imagine a particle like a little spinning top, but that's not quite right.
Hawking uses the analogy of a playing card, which I found helpful.
It's a great analogy. So a particle with spin 0 looks the same from every direction, like a dot. A spin 1 particle is like an arrow or a playing card. You have to turn it 360 degrees, a full circle, for it to look the same again.
Okay, that makes sense.
Correct. Then you have spin 2 particles, which look the same if you turn them just half a circle, 180 degrees. And then there's the weird one, spin 12.
The one you have to turn around 2 full circles, 720 degrees, just to make it look the same as when it started. That one always breaks my brain.
It is deeply counterintuitive, but spin 12 particles are what make up all the matter in the universe. Protons, neutrons, electrons, they are all spin 12.
Okay.
And because they are spin 12, they obey a very specific, very important rule called the Pauli exclusion principle.
And this is the why it matters moment, right? This is the big one.
This is maybe the most important why it matters moment for the existence of us, of structure.
The exclusion principle says that 2 identical matter particles cannot exist in the same state at the same time. So they can't be in the same position with the same velocity.
Exactly. They repel each other if you try to squeeze them too close. They demand their own space in a quantum sense.
So without this principle, matter would just squish.
It would collapse.
Hmm.
Without the exclusion principle, quarks wouldn't form separate protons and neutrons. Electrons wouldn't have their neat little orbits around the nucleus. They'd all just collapse into it. We wouldn't have atoms or chemistry or life. We would just be a dense, uniform soup. The exclusion principle is what gives matter its solidity. It literally keeps things apart.
Wow. Okay, so that's the matter. But what pushes and pulls the matter around? Hawking lists 4 fundamental forces, and he notes that the particles carrying these forces do not obey that exclusion principle.
Right, they're different. They have integer spins like 0, 1, or 2, and that means they can bunch up as much as they want.
Which is how you get a powerful force,
Exactly. So let's run through the 4 forces. First, you've got gravity.
which, surprisingly, Hawking says is the weakest force. By a lot.
It is incredibly weak. The gravitational pull between 2 protons is just minuscule, but it has 2 things going for it. It has a long range, and it's always attractive. It always adds up. So when you have a huge collection of particles, like a planet or a star, gravity becomes the dominant player.
Got it. Okay, number 2, the electromagnetic force.
Much, much stronger. About 1 with 42 zeros after it, stronger than gravity. It acts on charged particles, but, and this is key, it has both attraction and repulsion positive and negative charges.
So they tend to cancel out.
They cancel out on large scales. That's why the Earth doesn't electrically zap the moon. The pluses and minuses balance.
Then you have the 2 nuclear forces, which are more short range.
Right. The weak nuclear force, which is responsible for radioactivity, for certain types of particle decay, and then the strong nuclear force. That's the big one. That's the glue.
The glue holding quarks together in the proton and holding the nucleus together.
It's incredibly powerful, but only over tiny, tiny distances.
Mm.
Basically inside the nucleus of an atom.
And Hawking mentions this idea of confinement with the strong force. You can't just pull a quark loose, can you?
No, it's like a rubber band. The harder you pull, the stronger the force gets. And if you pull hard enough to snap the band, all the energy you put in just creates a new pair of quarks on the broken ends. You never, ever get a single isolated quark.
They're always in their little groups.
Always. So physicists have this dream of combining all these forces into one big theory, a grand unified theory, or GUT.
To find one master equation for most of everything.
Exactly. They're trying to merge the strong, weak, and electromagnetic forces. Gravity is usually left out of GUTs because it's so different. But one prediction of these theories is fascinating and a little terrifying: proton decay.
Yeah, this freaked me out a little.
Mm.
We think of protons as stable. They're the building blocks of
No,
the cube. But GUT suggests they might eventually just fall apart.
theoretically, yes. They might decay into lighter particles like anti-electrons, but, and this is a big but, don't panic, the predicted timescale is immense. Something like 1 followed by 30 zeros years.
Okay, good. So that's way, way longer than the current age of the universe. I won't cancel my weekend plans.
I wouldn't.
Okay, so we've got the particles and we've got the forces. Now, let's switch gears to Chapter 6, black holes.
The term black hole is actually pretty new. It was coined by the physicist John Wheeler in 1969. Before that, they had this much less catchy name, frozen stars.
Frozen star. Yeah, black holes better marketing. But the concept itself goes back way further. Hawking mentions guys like Mitchell and Laplace in the 1700s.
Right. Back then, they thought of light as particles, like tiny cannonballs. So they reasoned, what if a star was so massive and dense that its escape velocity was greater than the speed of light?
So even the light cannonballs couldn't get away.
Exactly. It was a theoretical curiosity. But to understand how one actually forms, we have to look at the life cycle of a star. And this connects right back to what we just discussed about forces. A star is a balancing act.
A balancing act between what?
Gravity trying to crush the star inward, and the thermal pressure from nuclear fusion, the heat from the star's engine pushing outward. As long as the star has fuel, hydrogen to burn into helium, it stays hot. And that pressure fights gravity to a standstill. It's stable.
But eventually the fuel runs out.
And when the fuel runs out, the star cools. The outward pressure drops. And gravity, well, gravity never turns off. It starts to win. The star collapses.
And this brings us to a really pivotal figure in the book, Subramanian Chandrasekhar.
Yes. In 1928, he was just a student sailing from India to England. On that boat ride, he did some calculations that changed everything.
On a boat. I feel so unproductive now.
He wanted to know, how big can a star be and still hold itself up against gravity after the fuel runs out?
He's that Pauli exclusion principle we talked about, right?
He did. He realized that as a star collapses, the electrons get squashed together. Because of the exclusion principle, they hate being in the same state, so they push back. This electron degeneracy pressure can support the star as a very dense object called a white dwarf. But Chandrasekhar calculated a limit.
The Chandrasekhar limit.
It's about 1.5 times the mass of our sun. If a dying star's core is heavier than that, the electron repulsion isn't strong enough. Gravity crushes it even further.
It could become a neutron star, which is even denser, held up by neutrons pushing back, but even that has a limit. And if the star is massive enough, nothing stops the collapse.
Nothing we know of. The star collapses catastrophically to a point of theoretically zero volume and infinite density. This is the singularity. It is a point where space-time is infinitely curved. And this is where the laws of physics, as we know them, break down.
And surrounding that singularity is the famous event horizon.
The point of no return. It's the boundary where the pull of gravity becomes so strong that even light, the fastest thing in the universe, cannot escape.
Hawking has this great analogy about the event horizon being like running away from the police.
Right. He says it's like you're running away and you manage to keep one step ahead, but you can never get clear. The light rays at the horizon are hovering right on the edge, trying to get out, but constantly being dragged back by gravity.
Now here is where it gets really interesting and mind-bending. The difference in perspective. Hawking describes an astronaut falling into a black hole versus someone watching from a spaceship far away.
This is pure relativity in action. Time is not absolute. It depends on gravity. So let's say the astronaut sends a signal back to the ship every second by their watch. Tick, tick, tick.
Okay.
As the astronaut gets closer to the event horizon, the massive gravity distorts time. To the person on the spaceship, those signals start arriving slower. What was 1 second apart becomes 2 seconds, then 10, then a year.
So if the astronaut falls in at 11.00 on their watch,
the observer on the ship sees the signals from, say, 10.59.59 stretch out for an eternity. They never actually see the astronaut cross the horizon. The image of the astronaut just gets redder and dimmer until it fades completely. They appear frozen in time just outside the hole.
But for the astronaut, what do they experience?
For them, time feels perfectly normal. They cross the horizon at 11.0 sharp. They don't feel a bump. There's no sign saying, "Welcome to the event horizon." They just pass through. But once they do, they can never send a signal back out. Their future is the singularity.
And their destiny involves spaghettification.
It's a vivid term, isn't it?
It's terrifying. Explain what that is.
It's caused by tidal forces. Gravity gets stronger the closer you are to the source. So if you fall into a black hole feet first, the pull of gravity on your feet is much, much stronger than the pull on your head.
Oh, I see where this is going.
The difference in force stretches you out lengthwise and squeezes you in sideways, like turning a person into a long strand of spaghetti.
Okay. Note to self. Do not fall into a black hole. But Hawking mentions that if the black hole is supermassive, you might actually survive crossing the horizon for a while.
Correct. For a really big black hole, the tidal forces at the horizon are gentler. You could cross without being torn apart immediately, but the spaghettification will get you eventually before you reach the singularity.
And that singularity, that point where physics breaks, really bothers scientists. Roger Penrose proposed something called the cosmic censorship hypothesis.
I love that name. God abhors a naked singularity.
What does that mean?
It's the idea that singularities, these points where our predictive power fails, are always hidden inside an event horizon. They're clothed, not naked. This protects the rest of the universe from the breakdown of predictability that happens there.
So it's a cosmic firewall.
In a way. But Penrose called it weak censorship. It protects us, the observers outside. It offers no such protection to the poor astronaut who falls in.
Right. Not much comfort for them. There's also this concept Hawking discusses called the no-hair theorem, which, again, physicists and their naming conventions.
It sounds funny, but it's profound. It means that once a black hole forms and settles down, it loses all the complex details of the star that made it. All the hair, the bumps, the composition, the magnetic fields is radiated away.
So what's left? What defines a black hole?
Just 3 things: mass, rotation, and electric charge. That's it. A black hole is a perfectly smooth, simple object. It doesn't matter if it was made from a star of antimatter or gold or old televisions. Once it collapses, all that information is lost. It is defined purely by how heavy it is and how fast it spins.
Okay, so we have all this amazing theory. But do we have proof? because for a long time, black holes were just math on a blackboard.
Right. You can't see them directly because they're black, but we can see how they affect things around them. Hawking discusses the prime candidate from back then, Cygnus X1.
And this is a system where we see a normal star, but it's orbiting.
Mm.
Nothing.
Exactly. It's orbiting an invisible partner. And by measuring the star's orbit, we can calculate that the partner is about 6 times the mass of the sun. It's too heavy to be a white dwarf or a neutron star. By elimination, it has to be a black hole.
And we can see stuff falling in.
That's the key. We see matter being ripped off the visible star, forming a disk around the black hole, getting superheated as it spirals in, and blasting out huge amounts of X-rays. That's what we detect.
And this leads to my favorite story in this section, the bet.
The Hawking-Thorne bet, a classic. In 1975, Stephen Hawking made a bet with another physicist, Kip Thorne, that Cygnus X1 did not contain a black hole.
Wait, Hawking bet against black holes. But that was his whole life's work.
He called it an insurance policy. He said, if it turns out black holes don't exist, all my research will have been for nothing. But at least I'll win the bet.
What was the prize?
A 1-year subscription to Private Eye magazine. He was hedging his bets on his entire career for a magazine subscription.
That is hilarious. So what happened?
The evidence became overwhelming. By the early 90s, he had to concede. He famously broke into Thorne's office while he was away, found the framed bet, and signed it with a thumbprint to acknowledge that he lost. Black holes were real.
What a great story. So what does this all mean? We've gone from quarks, they're governed by the exclusion principle, to stars that collapse into a point where that principle is just obliterated.
It's the story of structure versus collapse. The Pauli exclusion principle keeps the tiny particles apart, giving structure to atoms and stars and us. But gravity is relentless. If you pile up enough matter in one place, gravity overwhelms that exclusion. The structure fails. The star collapses into a black hole.
And we end up with a singularity, a point where space and time as we understand them just stop.
And that is the provocative thought to leave with today. If the laws of science break down at the singularity, how can we ever have a complete theory of the universe? If there's a point where the rules just don't apply, are we missing something fundamental?
That is a little unsettling. But reading ahead, I think Hawking hinted that maybe black holes aren't the absolute end of the story.
He certainly did. That was his next great breakthrough.
And in the next part, we will uncover why black holes aren't as black as we thought and explore the ultimate origin of everything in black holes ain't so black and the origin and feet of the universe. You do not want to miss that.
It changes everything we thought we knew about them. It's a game changer.
I'm your host, ready to ask the questions you're screaming at your phone, and with me is our expert guide to keep us from falling into a wormhole.
It's great to be back. And frankly, if we do our job right today, falling into a wormhole might seem like the easy part of physics compared to what we are about to cover.
That is ominous, but I like it. So let's set the stage. If you've been with us for the previous parts, we have built up a very specific, almost terrifying picture of the universe.
We have, yes.
We've talked about the expanding cosmos, the warping of space-time, and in the last session, we left off on a pretty dark note with black holes.
We did. And up until now, we've been operating largely under the rules of classical general relativity. That's Einstein's theory of gravity.
Right.
And under those rules, black holes are the ultimate dead end. They are the roach motels of the universe. You check in, but you never check out.
Right. Abandon all hope, ye who enter here. The event horizon was the finish line of existence. Once you cross it, you are cut off from the rest of the universe forever. It's a one-way ticket.
Exactly. That is the classical view. But today we are at this massive turning point in the source material. We're flipping the script.
Okay.
We are moving from the realm of the very large gravity, stars, galaxies, into the realm where that large-scale physics has to shake hands with the very small
Quantum mechanics.
Quantum mechanics. And usually these two theories hate each other.
They do not get along at all. It's like the biggest family feud in all of science.
It really is. They rely on fundamentally different assumptions about reality. But to understand black holes and to really understand the Big Bang, you have to force them into the same room.
And when you do that,
and when you force general relativity and quantum mechanics to talk to each other, things get weird.
Weird is an understatement. I've looked at the notes for today, and we are unpacking two paradoxes that frankly sound impossible. First, that a black hole, literally defined by being black and trapping everything, can actually glow.
Yes.
And second, that the universe can have a beginning without actually having a starting edge.
Yeah.
Which My brain just rejects that sentence.
It's the search for the synthesis. We're going to explore the life cycle of black holes, which turns out to be dynamic and volatile, and we are going to look at the boundary conditions of existence itself.
So, buckle up. We are going to the edge of time today. Let's start with Chapter 7, Black Holes Ain't So Black. To really understand why this was such a revolution, I want to go back to the history. Because science isn't just equations floating in the void, it's people.
It is.
And this starts with a very specific evening in November 1970.
It does. It's a very human moment in the book. Hawking describes getting into bed. Now, we have to remember, by 1970, his disability from ALS was progressing. This wasn't a quick jump into pajamas.
Right.
It was a slow, deliberate process.
And he mentions that this slowness actually gave him time.
Exactly. He couldn't rush, so his mind was free to wander. And on this particular night, shortly after the birth of his daughter Lucy, as he was slowly getting ready for sleep, he started visualizing the geometry of black holes. He had a sudden realization about the event horizon.
Okay, so just to refresh everyone's memory, because it's been a week for the listener, the event horizon is the point of no return. It's the edge of the shadow where gravity becomes so strong that it pulls even light back in.
Precisely. It is the boundary. And Hawking realized something about the light rays that form that boundary. He realized that the paths of light rays that just fail to escape must be moving parallel to each other.
Parallel.
They're hovering right on the edge, racing outwards, but never getting anywhere, like running on a treadmill.
Okay, I'm visualizing this. They are trying to get away, but gravity is holding them perfectly in place.
And here was the kicker. Hawking realized these light paths can never approach each other.
Why not?
Well, if they did, they would eventually run into one another, and if they ran into one another, they would merge and fall in.
And if they fell in, they wouldn't be the boundary anymore. They'd just be more stuff that got caught.
You've got it.
Yeah.
So geometrically, the light rays defining the edge can never get closer together. They can only stay parallel or move apart.
Okay, so what does that mean in, like, real-world terms?
Well, let's unpack what that means physically. If the rays that make up the skin of the black hole can never get closer, it implies that the total surface area of the event horizon can never decrease.
Wait, hold on. Never decrease.
Mhm.
So it can stay the same, or it can get bigger, but it can never, ever shrink.
In classical theory, yes, that was a breakthrough. Think about the logic. If matter falls into the black hole, the mass increases, gravity gets stronger.
The hole gets bigger. The area increases. Okay, that makes sense. You feed it, it grows.
Right. Now imagine two black holes collide and merge. You have two event horizons becoming one.
What happens then?
Hawking proved that the area of the new combined event horizon must be greater than or equal to the sum of the areas of the original two.
So 1 + 1 equals something slightly more than 2, or at least 2.
Essentially, the shadow only gets bigger. It is a one-way process.
Okay, so we have a rule. The area of a black hole only increases.
Why was this a eureka moment? It sounds like just a geometry proof.
Because it rang a bell. A very loud, specific bell in the world of physics. This behavior, always increasing, looked suspiciously like another famous law.
Don't tell me. Let me guess. Entropy.
Concept of entropy.
Ah, entropy. Now, you mentioned this word, and I feel like it gets thrown around a lot. I hear it used for everything from messy bedrooms to corporate restructuring to heat death of the universe. But in this specific physics context, what are we actually measuring? It's the measure of disorder in a system. Or, more accurately, the number of internal states a system can have while looking the same from the outside. But disorder is the easiest way to visualize it.
Okay, give me the classic example.
The coffee cup. If you have a pristine coffee cup on your table, it is in a state of high order. The molecules are arranged in a specific lattice structure. It's very particular.
And if I knock it off the table,
It shatters. Now you have shards on the floor. That is a state of disorder. There are millions of ways the pieces could be arranged on the floor. That's high entropy. There is only one way it can be a cup that's low entropy.
and the second law of thermodynamics says,
It says that in any closed system, entropy always increases. Things naturally get messier. You never see the shards jump back up off the floor and reassemble themselves into a cup.
right, the movie never runs backward. Order degrades into disorder.
So Hawking sees that the area of a black hole behaves just like entropy. Area always goes up. Entropy always goes up.
Exactly. The parallels were undeniable. But here is the problem. It created a massive paradox.
No. Suppose you have a system with a lot of entropy, let's say a box of hot gas, where the molecules are flying around chaotically. That's a very disordered system.
Okay, I have my chaotic box of gas.
Now you throw that box into a black hole.
It's gone. It crosses the event horizon and vanishes from the observable universe. Poof.
Right. And if the matter is gone, the entropy is gone. You have effectively removed messiness from the universe. The total entropy of the universe outside the black hole seems to have gone down.
Which violates the second law of thermodynamics.
It breaks the law, one of the most fundamental laws in all of physics.
So wait, if I'm understanding this correctly, black holes were looking like a cosmic loophole, a cheat code. I could just sweep all the dust and broken cups in the universe under the black hole rug, and suddenly I've lowered the entropy of the cosmos.
That is exactly the implication. It seemed like a violation of the fundamental laws of physics, and nature does not like cheat codes. Hawking and the community knew this was a problem, but they didn't have a solution.
Enter the challenger.
Yes. A young research student at Princeton named Jacob Bekenstein.
I love this part of the story because it feels like academic drama. You have Hawking, the established genius, and the student Bekenstein. And Bekenstein comes up with a bold idea.
A very bold idea. Bekenstein suggested that the area of the event horizon was the measure of its entropy. He said, effectively, you didn't destroy the entropy when you threw the box in, you just transferred it to the black hole.
So the black hole keeps the score. The bigger the area, the more entropy it holds.
Precisely. The accounting balances out. The second law is saved.
It makes perfect sense, visually. Matter falls in area, entropy falls in area, it gets bigger, it all adds up. So why was Hawking annoyed? The book explicitly says he was irritated.
Because Bekenstein's idea had a fatal flaw, or what Hawking thought was a fatal flaw. You see, if a black hole has entropy, then, according to the laws of thermodynamics, it must have a temperature.
Okay.
And if an object has a temperature, it must emit heat. It must radiate energy.
Ah, I see the problem. That's a huge problem.
It's a deal breaker. If it radiates, it isn't black. We just spent the last episode defining a black hole as something that lets nothing escape.
Right. The name is black hole, not glowing gray orb.
Exactly. So if Bekenstein is right, black holes glow. If black holes are truly black, Bekenstein must be wrong.
So Hawking sets out to destroy this theory. He sits down to do the math, presumably to prove that black holes are strictly one-way streets, and that Bekenstein was just using a sloppy analogy.
That was the plan. He decided to apply quantum mechanics to the space just outside the event horizon to settle the debate once and for all. He wanted to calculate exactly what happens to particles in that extreme gravity.
He wanted to prove silence, but the math started screaming.
It did. When he finished the calculation, he found something shocking. He found that Bekenstein was right. The math showed that the black hole wasn't just sitting there. It was emitting particles. It was glowing.
This is the famous Hawking radiation. This is the moment where black holes ain't so black.
Yeah.
But we need to slow down here because this is the hardest concept in this chapter. We just said gravity is infinite at the singularity and nothing escapes the horizon. How does something get out of a prison that's, inescapable by definition?
To understand this, we have to stop thinking about space as empty. We usually think of a vacuum as a void, a whole lot of nothing.
Right, the absence of everything.
But quantum mechanics, specifically the uncertainty principle, tells us that space is never truly empty.
It's teeming with activity, right? It's alive.
In a way, it is filled with what we call virtual particles.
Virtual makes them sound like computer code or something not quite real. What are they actually?
They are pairs of particles and antiparticles, so an electron and an antielectron, which is a positron, or a photon and an antiphoton, which is just another photon.
Okay, so they come in pairs.
Always in pairs. They pop into existence literally out of nowhere, borrowing energy from the vacuum itself. They separate briefly, then snap back together and annihilate each other.
So they appear, kiss, explode, and vanish.
A perfect description. And they do this incredibly fast, so fast that we can't detect them directly with a Geiger counter. That's why they are virtual. But we know they exist. We can measure their effects on other things, like the tiny shifts in the energy levels of atoms.
That's the Seymour effect and all that.
Exactly. So space is a bubbling, frothing soup of these popping particles. Usually they cancel out. But what happens when this dance occurs right on the edge of a cliff? Right on the event horizon?
That's the game changer.
That's the game changer. Imagine a pair pops into existence right at the boundary. One particle is just inside the horizon, and the other is just outside.
Okay. The one inside is doomed. It's on the wrong side of the track.
It's captured. It falls toward the singularity, no hope of escape. But now look at the partner. The partner is on the outside.
It's been stood up. Its dance partner is gone forever.
Chuckles, exactly. The divorce is final. The partner that fell in is gone. It can't come back to annihilate the one on the outside.
So the outside particle is stranded. It's an orphan.
Right. And now it has a choice. It can follow its partner into the abyss, or if it has just the right trajectory, it can escape. It shoots out away from the black hole into the rest of the universe.
Okay, wait. I want to look at this from the perspective of an astronaut with a telescope a million miles away. What do I see?
You don't see the complex quantum divorce happening at the surface. You're too far away. All you see is a particle, a photon, a neutrino, whatever, zooming out of the black hole.
Which looks exactly like the black hole is spitting something out, like it's leaking.
Precisely. It looks like thermal radiation. But here is the headache, the real headache that trips people up. That escaping particle has energy. It has mass. It's now a real particle, not a virtual one.
Right. And there is no free lunch. That's rule number 1 in physics. You can't just create energy out of nothing. If a new particle appears in the universe, the energy bill has to be paid.
So who pays the bill?
I'm guessing the black hole.
The black hole pays. And the currency it pays with is its own mass. This is the negative energy concept. This is the part that usually confuses people, so let's break it down.
Please. Because how can a particle have negative energy? I thought energy was mass, E equals mc squared. How do you have negative mass?
You have to think about energy in terms of debt and assets. Gravity is attractive. To separate two things that are attracted to each other, like lifting a rock off the earth, you have to put energy in. You have to do work.
Okay, I lift the rock, I burn calories,
Yeah.
I add energy to the rock-earth system. The rock now has more potential energy.
Right. So, conversely, if you are close to a massive object, you have less energy than if you were far away. You are in an energy well. You're in a state of energy debt to gravity.
Okay, I'm in debt to gravity. That makes sense.
Exactly. Now, inside a black hole, the gravity is so strong that this debt is massive. It is possible for a particle inside the hole to have so much gravitational debt that its total energy, when you add it all up, is negative.
Whoa. So let's track the pair again. We have two virtual particles. They pop into existence together, so their combined energy is 0.
Correct. Zero-sum game.
They separate. The one that escapes becomes real. It has positive energy, positive mass. It flies off into my telescope.
Correct. And to balance the books of the universe, where total energy must remain constant, the one that fell in must have negative energy.
So the black hole swallows the negative particle.
It swallows a unit of negative energy,
Hmm.
and when you add a negative number to a positive number, what happens?
The total goes down.
So by eating the negative particle, the black hole loses mass. It loses weight.
Wow. Okay, so the black hole pays the energy bill for the particle that escaped by consuming its negative energy twin. The consequence is that the black hole is shrinking. It is evaporating.
That's it. That's Hawking radiation. It's a slow, particle-by-particle leak of mass energy back into the universe.
This completely changes the narrative. We started the series saying black holes are eternal prisons. Now you're saying they leak.
Yeah.
And if they leak, do they eventually die?
They do. They have a life cycle. And the speed of that life cycle depends on their mass. This is counterintuitive, so bear with me.
I'm ready.
Large black holes are very, very cold. They emit very little radiation. A black hole with the mass of our sun would leak energy incredibly slowly. It would take countless eons, longer than the current age of the universe, to evaporate.
Because the slope of gravity at the edge isn't as steep? Is that a fair way to think about it?
Roughly speaking, yes. The curvature of spacetime is less extreme at the horizon of a supermassive black hole. But a small black hole, a tiny one, say the mass of a mountain,
It's hot.
it is white hot, it radiates furiously.
And as it radiates, it loses mass.
And as it loses mass, it gets smaller.
And as it gets smaller, it gets even hotter.
It's a runaway process. It accelerates. The last few moments of a black hole's life are a catastrophe. It disappears in a tremendous final burst of emission.
How big a burst are we talking?
Hawking calculates it would be the equivalent of millions of hydrogen bombs going off at once. A final, spectacular flash of gamma rays and other particles.
That is a spectacular way to go, just popping out of existence in a blaze of glory. Now, the book mentions that we haven't actually seen one of these explosions yet.
No, we haven't. And that tells us something important about the universe. If there were primordial black holes, tiny ones created in the pressure cooker of the Big Bang, those with a certain mass, about 1 billion tons, the mass of a large mountain.
They would be reaching the end of their lives right about now.
Exactly. Their 15 billion year lifespan would be up. But since we aren't seeing gamma ray bursts constantly going off in our neighborhood, we know there's a limit to how many of these things can exist.
It puts a constraint on our theories of the early universe.
It does. But the key takeaway here is the synthesis. By applying quantum mechanics with its virtual particles to general relativity's black holes, we removed the blackness. We proved they leak, they glow, they evaporate, they're not eternal.
Which is a perfect segue to the next massive topic. If quantum mechanics changes the fate of a black hole, the end of time for a star, what does it do to the Big Bang? The beginning of time for the entire universe.
This is the focus of Chapter 8. We are pivoting from the end of time to the origin of time.
In previous episodes, we talked about the singularity. The idea that if you run the film of the universe backward, everything contracts until it is infinitely dense and infinitely hot at a single point.
Right. Classical general relativity predicts a singularity at the beginning. But remember what we said about singularities inside black holes. They are points where the laws of physics break down.
Science basically throws up its hands and says, I don't know. The equations give you infinity, which means the equations are broken.
And that is deeply unsatisfying for a physicist. If the laws of science break down at the beginning, then you cannot predict how the universe started. You have to assume that a creator or some external agency set the initial conditions arbitrarily.
It's the tortoises all the way down problem again. It forces us to ask, what happened before the beginning? And if there was a singularity, the word before doesn't even make sense.
Correct. Time itself begins there. So, Hawking wants to see if quantum mechanics can rescue us from the singularity at the beginning, just as it modified the black hole.
And to do that, we first need to look at the standard hot Big Bang model and why the universe looks the way it does today.
Exactly. We know the universe is expanding and cooling, so it must have been unbelievably hot and dense in the past.
Right.
And as it cooled, interesting things happened. The book uses the analogy of water freezing to explain a concept called symmetry breaking.
Let's unpack that, because water freezing sounds simple, but the physics is deep.
Think about liquid water. It is symmetrical. If you float in a tank of water, it looks the same in every direction. There is no preferred access, no special orientation.
Right, it's uniform and isotropic.
But when it freezes into ice, it forms crystals. Those crystals have lines, structures, specific orientations. The symmetry is broken. It is now rigid and directed.
It picks a direction.
It picks a direction. And in the early universe, this freezing wasn't water turning to ice. It was the forces of nature themselves differentiating.
What do you mean by that?
At super high temperatures, physicists believed the strong nuclear force, the weak nuclear force, and electromagnetism were likely all one unified superforce.
They were all symmetrical, indistinguishable.
Exactly. But as the universe cooled, they separated out. They froze into the distinct forces we see today. The symmetry was broken.
Okay, that makes sense. But there's a puzzle here, the uniformity puzzle. When we look at the cosmic microwave background radiation, that afterglow of the Big Bang, it is incredibly smooth. The temperature is the same to 1 part in 100,000 in every direction we look.
Which is strange for a standard explosion. Explosions are usually messy, chaotic, and lumpy. If you set off a grenade, you don't get a perfect sphere of expanding gas.
No, you get shrapnel here, a gap there, it's a mess.
So if the Big Bang was just a bang, the universe should be lumpy. Some parts should be super dense, some parts nearly empty, but instead, it looks perfectly ironed out.
So what's the solution?
Enter Alan Guth and the theory of inflation. This was a major addition to the Big Bang model in the 1980s.
Inflation. Not the economic kind, thankfully.
Definitely not. Guth suggested that very early on, for a tiny fraction of a second, the universe went through a period of super rapid expansion. Exponential expansion.
The book says it expanded by a factor of 1,000,000,000,000,000,000. Basically, a 1 with 30 zeros after it. Yeah. In a fraction of a second. So small, I can't even see the number.
Think of it like a balloon. If a balloon is wrinkled and small, and you blow it up incredibly fast to an enormous size, what happens to the surface?
The wrinkles get stretched out. Any little crinkle on the surface is just gone. The surface becomes incredibly smooth.
Exactly. Inflation explains why the universe looks the same in all directions. It took a tiny, uniform patch of the early universe and blew it up to be the size of the whole observable cosmos. It smoothed out all the lumpiness.
So inflation fixes the lumpiness problem. But does it fix the singularity problem? Do we still have that sharp, nasty point at the beginning where math fails?
Yes. Even with inflation, the singularity remains in the classical model. We still have a beginning where time starts abruptly. And that brings us to Hawking's most famous and Controversial proposal.
The no-boundary proposal.
A no-boundary proposal.
This is where we have to talk about imaginary time, and I have to be the skeptic here. When I read imaginary time, my brain immediately thinks fake time, like made-up pretend time.
It is a terrible marketing name for a very real mathematical concept. It's an unfortunate historical label from the world of complex numbers. It doesn't mean make-believe.
So help me visualize it. If it's not fake, what is it?
Think of real time, the time we experience, as a horizontal line going from left to right. You can move forward into the future or look back at the past. It's a railroad track. You are stuck on the rails.
Okay, stuck on the tracks. I get that.
Now imagine a direction perpendicular to that track, up and down, a direction at a right angle to the normal flow of time. That is what mathematicians call an imaginary direction.
So it's just another dimension, like width or height.
In a mathematical sense, yes. Think of an airplane. A car is stuck on the road, which is like a one-dimensional line. That's our experience of real time. But a plane can pull up. It can move in a dimension that the car cannot.
So if you use imaginary time in your equations, you aren't stuck on the timeline anymore.
Right. And here is the magic trick. In standard physics, time is fundamentally distinct from space. But if you do the math using imaginary time, the difference between time and space disappears. Time just becomes another spatial dimension.
This is what he calls Euclidean space-time.
Yes. In this state, the universe has 4 dimensions of space and no distinct dimension of time. And this allows us to visualize the beginning of the universe in a completely new way. We need the Earth analogy here. It is crucial to understanding the no-boundary idea.
Okay, let's walk through it. I want the listener to picture the Earth, a globe sitting on a desk.
Imagine the history of the universe is the surface of that Earth. The North Pole represents the Big Bang, the very beginning.
Okay, so I'm standing at the North Pole. Time starts here.
As you walk south, away from the pole, the circles of latitude get bigger and bigger. The Earth gets wider.
That represents the universe expanding as time goes on. The further south I go, the later in time it is, and the bigger the universe is.
Right. Now look down at your feet at the North Pole. What is there?
Ice. A point on the map. It's just a place.
Is it a cliff? Is it a jagged edge where the Earth falls away? Is it a singularity where the laws of geometry break down?
No. It's just a point.
Yeah.
It's the same as any other point on the globe, fundamentally. I can walk across it. The lines of longitude all meet there, but nothing breaks. It's perfectly smooth.
Exactly. Now, here is the million-dollar question. What is north of the North Pole?
Nothing. The question doesn't make sense.
But is nothing a void? Is it an edge you can fall off of?
No. It's just that the direction north ceases to exist once you're at the pole.
Yeah.
It's a grammatical error to even ask.
Precisely. The Earth is finite. It has a specific surface area, but it has no boundary. There is no edge where you fall off.
So Hawking is saying the universe is the same way.
That is the proposal. The boundary condition of the universe is that it has no boundary.
So in imaginary time, the universe is a self-contained, four-dimensional sphere. It didn't begin in a singular explosion where physics broke down. It just closes up, like the tip of a shuttlecock or the North Pole of the Earth.
It's smooth at the bottom.
This is huge. Because if this proposal is correct, the singularity disappears. The laws of science hold everywhere, even at the very beginning.
This solves the predictability problem. You don't need to appeal to an outside agent to set the initial rules at the singularity because there is no singularity.
And this leads us directly into the theological implications that Hawking discusses in Chapter 8. He is very direct about this, which I found surprising for a physics book.
It is surprising, but it's the logical endpoint of the idea. He basically sets up a flow. If the universe has a sharp beginning, a singularity, then it implies a moment of creation.
Right. A moment where someone had to light the fuse. You need an explanation for what came before, what caused it.
But if the universe is like the Earth's surface, completely self-contained, no edge, no beginning in that sharp, singular sense, it simply is. It doesn't need to be created or destroyed. It just exists.
And he drops that famous line, which is worth quoting in full.
Yeah.
So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place, then, for a creator?
It's a provocative question. He isn't necessarily saying God doesn't exist, but he is saying that the job description of setting the initial conditions is no longer vacant. The universe manages its own birth through the laws of physics.
It crowds out the need for divine intervention at that specific moment.
It pushes the explanation back to the laws themselves. Why are the laws of physics what they are? That's the new question.
Now, we can't talk about the origin of the universe without hitting the anthropic principle. We touched on this briefly in previous episodes, but it really shines here as an explanation for why we are here.
It does. The core question is, why is the universe the way it is? Why are the fundamental constants of physics just right for life to exist?
Right. If the electron charge were slightly different, stars wouldn't burn. If the strong nuclear force were a little weaker, we wouldn't have atoms beyond hydrogen. If gravity were slightly stronger, the universe would have collapsed back on itself instantly.
It's the Goldilocks universe. Everything is tuned just right.
So how do we explain that?
The weak anthropic principle basically says, we see the universe this way because if it were different, we wouldn't be here to see it.
It sounds like a tautology, like saying, I'm here because I'm here. It feels a bit like cheating, doesn't it?
It does feel cheap at first,
Yeah.
but it's also a valid explanation for what we call selection bias. Imagine there are infinite universes, a multiverse. Most are chaotic, dead, too hot or too cold.
Barren wastelands.
Exactly. We, as conscious observers, obviously find ourselves in the rare pocket that allows for life because we are alive.
We couldn't very well find ourselves in one of the dead zones asking, why is it dead here?
Yeah.
Because we'd be dead.
Precisely. But what is fascinating is that Hawking connects this to the no-boundary proposal. The calculations suggest that a universe with no boundary would likely start with the kind of critical expansion rate, that Goldilocks rate, that allows for galaxies and stars to form over billions of years.
So the math of the no-boundary proposal actually predicts a universe that looks like ours. You're a life-friendly one.
It does. And more than that, it predicts that the universe should start out very smooth, but with tiny quantum fluctuations, tiny ripples in the smoothness.
Which are the seeds for?
The seeds for galaxies. Those slightly denser regions eventually clump together under gravity to form stars and galaxies. And in 1992, the COBE satellite actually measured these ripples in the cosmic microwave background.
And they matched the theory.
They matched the predictions of the no boundary and inflation theories remarkably well. Hawking called it seeing the fingerprints of creation.
That is incredible. So let's try to synthesize all of this, because my brain is starting to melt a little. We started with black holes leaking and evaporating. We ended with the universe having no beginning. What is the common thread here?
The common thread is the smoothing effect of quantum mechanics.
How so? Explain that.
Classical general relativity is sharp. It deals in points, singularities, hard edges. It predicts infinite densities at the center of black holes and at the beginning of time. It breaks things.
And quantum mechanics is fuzzy.
Exactly. It's based on the uncertainty principle. It introduces uncertainty, a kind of fuzziness. It smears things out. When you apply that smearing to the event horizon of a black hole, particles can tunnel out. The sharp edge of the prism becomes porous.
And when you apply it to the Big Bang,
The sharp point of the singularity gets smoothed out into a rounded cap, like the North Pole on the globe. The infinite density becomes finite. The breakdown is avoided.
so the synthesis of the very big general relativity and the very small quantum mechanics basically saves the universe from breaking down at its most extreme points.
That's a beautiful way to put it. It restores predictability. It suggests that the universe is governed by a rational set of laws that we can discover, and those laws hold everywhere, from the beginning to the end.
But there is a catch, and we have to be honest about this. We are relying on imaginary time to make this work. What does that mean for us here in our everyday lives?
Yes, and Hawking offers a final, crucial caution here. In real time, the time we experience, where clocks tick forward and we get older, the universe does appear to have a beginning. The Big Bang's singularity is still there in our perceived history.
But in imaginary time, which might be the underlying mathematical structure of reality, it's smooth and has no boundary.
So which one is real? Hawking would say that's the wrong question. He'd ask, which one is the more useful description? If imaginary time explains why the universe is the way it is, why it has the properties we observe, then maybe it is the more fundamental reality.
That is a lot to process. The idea that time running at right angles to itself is the reason we exist.
It's humbling. We are peeling back the layers of reality and finding that our common sense, our linear, forward-marching view of time may just be an illusion or a limited perspective of a much richer, stranger structure.
Well, speaking of the linear view of time, that is the perfect setup for our next deep dive.
It certainly is. We've talked about the beginning and the end. Next time, we are going to talk about the flow, the direction.
In the next part, we will travel through time and understand why we remember the past, but not the future, in the arrow of time and wormholes and time travel. We'll get into why cups break but not unbreak.
We'll tackle why time seems to only run one way, and if we can ever cheat it. Can we build a time machine? Hawking has some very specific thoughts on that.
I cannot wait for that one. Thank you for listening to this deep dive into glowing holes and the edge of time. It's been a trip.
A trip through imaginary time, you could say.
We'll see you in the next one.
Today, we are stepping into some truly, truly mind-bending territory. I mean, we've been journeying through the cosmos, looking at stars, the shape of the universe.
The big picture stuff.
The big picture stuff. But today we're looking at something that affects every single one of us, every single second of the day. Time.
It's fun, isn't it? It is the most familiar concept in our lives, and yet, when you actually try to pin it down with physics, it becomes the most elusive.
Exactly. And that's what we're doing. In part 5, we discuss chapters, the arrow of time, and wormholes and time travel.
These are, I would argue, the most speculative and, philosophical chapters of Hawking's work. We are really moving from the structure of the universe to the flow of reality itself.
And before we get lost in the time vortex, welcome to Fact Horizon. In this series, we break down the seminal work, A Brief History of Time by Stephen Hawking, exploring the nature of the cosmos from the Big Bang to black holes.
And today, we are asking the questions that, they keep people up at night. Why can we remember the past, but not the future?
Yeah, that's a big one. And why do broken cups never gather themselves back together?
And maybe the most exciting one, can we ever cheat the system?
Can we build a time machine?
When we build a time machine.
I have been waiting for this one. Time travel. It is the ultimate sci-fi dream. But what I love about this source material, this book, is that Hawking doesn't treat it like magic.
No, not at all.
He treats it like a physics problem.
A very, very difficult physics problem,
Yeah.
but a physics problem nonetheless. And before we can even talk about shortcuts through time, what we call wormholes, we have to understand why time seems to have a direction at all.
Right. Because to me, it feels obvious. Yesterday happened, tomorrow hasn't. Time flows forward. End of story. But you're telling me the laws of physics don't necessarily agree.
And that is the great mystery. When you look at the fundamental laws of science, general relativity, for gravity and quantum mechanics, for the tiny stuff, they are remarkably symmetric.
Symmetric meaning? They don't care which way the clock runs.
Precisely.
Yeah.
We have these mathematical operations we call symmetries. There's C, which stands for charge, so you swap a particle for its antiparticle.
Okay.
There's P for parity, which is like taking a mirror image of the universe. And then there is T time.
T for time.
If you take the laws of physics that describe how, say, two particles bounce off each other, and you just reverse the motion, you run the film backward, the laws still hold.
The math still works.
The math works out just fine. A particle moving backward in time looks exactly like an antiparticle moving forward. The equations do not care about past versus future.
Okay, so if I'm an electron, I don't care about tomorrow or yesterday, but I am not an electron. I'm a human being, and if I drop my favorite coffee mug on the kitchen floor, it shatters.
And that is the classic example Hawking uses, the broken cup.
It's such a visceral image. You watch that cup fall, it hits the tile, it shatters into 100 pieces, coffee splashes everywhere. It's a mess.
Now, imagine you filmed that event, and then you played the video backward. What would you see?
I'd see the coffee rushing back into the center. I'd see the little shards of ceramic just lifting off the floor, fusing perfectly back together, and the whole cup would jump back onto the table.
And what would be your reaction to seeing that?
I'd say that's fake,
Yeah.
or that's a movie trick, because that never, ever happens in real life.
Exactly. You instinctively know that the backward film is wrong. In our day-to-day life, there is a massive, undeniable difference between the past and the future. The past is ordered, the cup on the table. The future is disordered, the cup in pieces on the floor.
So if the laws of physics say forward and backward are the same, what is forcing the cup to break and never unbreak? What's the hidden rule here?
The culprit is the second law of thermodynamics.
Ah, the second law. I feel like this is the law that governs my entire life.
It governs everyone's life. It's the one that states that in any closed system, entropy always increases.
And entropy is just a fancy word for mess, right? For disorder.
That's a great way to think about it. To be a little more precise, it's a measure of disorder, yes, but specifically it's about probability and the number of states something can be in. Hawking puts it essentially as a form of Murphy's Law.
Things tend to go wrong.
Things tend to go wrong. Things tend to get messier.
Okay, but let's drill down on this probability aspect because I think that's where the magic trick happens. Why does probability care about my cup?
Okay, think about the arrangement of all the atoms in the cup. There is really only one specific arrangement, or maybe a very small set of arrangements, where all those atoms form a nice whole cup sitting on a table.
Right. It has to be that specific shape to hold coffee. The handle has to be attached. The bottom has to be sealed. We call that the macroscopic state of being a cup.
Exactly. But now think about the broken state. How many different ways can you arrange those same atoms so that the cup is shattered on the floor?
I mean, in millions, billions. It feels infinite.
Practically infinite. You could have 3 big pieces and 1,000 tiny shards. You could have it ground to dust. You could have the pieces scattered in the corner or under the fridge. There are trillions upon trillions of possible arrangements of atoms that all qualify as broken cup.
So just by pure chance, it is overwhelmingly more likely for the atoms to end up in one of the trillions of broken states than in that one single whole state.
Exactly. If you just let things evolve randomly, if you shake the box of the universe, so to speak, you will inevitably drift from a state of low probability, which is order, to a state of high probability, which is disorder. That drift is what we perceive as the flow of time.
So time isn't some fundamental train track laid down by the universe. It's just a statistical accident. We are literally just watching things get messier.
In a very real sense, yes. It's strictly a numbers game. It is theoretically possible for all the atoms of the broken cup to randomly vibrate in just the right way to leap back onto the table and reassemble themselves. The laws of physics allow for that.
But don't hold your breath.
You would have to wait longer than the entire age of the universe for that to happen by chance, even once. So, for all practical purposes, the arrow only points one way, toward disorder.
This brings us to what Hawking identifies as the 3 arrows of time. He says there are 3 distinct ways to measure forward. Let's unpack those.
Right. So first we have the thermodynamic arrow. This is what we just discussed. It's the direction in which disorder or entropy increases. It's why the cup breaks. It's why your coffee gets cold. The ordered heat energy spreads out into the disordered, colder room.
Okay, that's arrow number 1, the arrow of mess, the statistical arrow. What's number 2?
The second is the psychological arrow. This is the one we feel. It's the direction in which we feel time pass. It's the reason you remember the past, but not the future.
Which feels very different. One is about physics and cups breaking. The other is about my brain and my subjective experience of consciousness.
It seems different, but we'll get to how they connect in a moment.
Yeah.
And trust me, that connection is the linchpin of this entire argument. But let's define the third one first. The cosmological arrow. This is simply the direction in which the universe is expanding rather than contracting.
So the universe getting bigger is also a kind of clock. It's another forward direction.
It defines a direction, yes. Expanding is forward. Contracting would be the opposite. So the big question Hawking poses is, why do all 3 of these arrows align? Why do we remember the past, psychological, in the same direction that the cup breaks, thermodynamic, and in the same direction that the universe expands, cosmological?
Yeah, why? Is it just a massive coincidence? Could I live in a universe where I remember tomorrow, but cups still break and the universe is still expanding?
Hawking argues it's definitely not a coincidence. Let's look at the link between the first 2, which I think is the most profound part, the arrow of entropy and the arrow of memory.
This was the part of the text that really made me just stop and think. He basically claims our memory is powered by entropy.
It is. It really is. He uses this brilliant analogy of a computer memory. Imagine you want to record a memory, let's say saving a file on your hard drive, or even something simple, like using an abacus.
An abacus is a good visual, sliding beads around on a wire.
Okay, so before you record the memory on the abacus, the system is disordered. The beads are scattered randomly all over the place. Or in a computer, the magnetic bits are flipping randomly.
Okay, so it's in a high entropy, messy state.
To record a memory, you have to force the system into a very specific, ordered state. You move all the beads to the left side. You align the magnetic bits to read 1010. You are creating order.
But wait a second, didn't we just say the universe loves disorder? If I'm creating order in my brain or on my computer, am I not violating the second law?
That is the crucial question. And the answer is no, because you're creating local order. But here's the catch. To move those beads or to flip those bits, you have to expend energy. You have to do work.
Right. I have to physically move the bead with my finger. Or the computer has to use electricity from the wall.
And what happens to that energy? It doesn't just vanish. It turns into heat.
My computer fan spins up, my muscles burn a little glucose, and I get warm.
Exactly. And that heat is disordered energy. It dissipates into the room, jiggling the air molecules randomly, increasing the entropy of the surroundings.
I see where this is going.
The math shows, and this is the key, that the amount of disorder you create in the universe by generating that heat is always greater than the tiny bit of order you gained by storing the memory.
So the net result for the universe is always more mess.
Always.
Yeah.
Every time. You pay for your memories with entropy. You cannot form a memory. You cannot think a thought without increasing the total disorder of the universe.
That is it's profound. We remember the past because the physical act of remembering is part of the process of the universe getting messier. Our subjective sense of time is literally locked to the thermodynamic arrow.
Precisely. And if the thermodynamic arrow were to reverse, if cups started unbreaking, our brains would have to operate in reverse too. We wouldn't be able to watch the cup unbreak because our memory formation itself would be running backward. We would be unremembering things.
That's a headache just to visualize. But it effectively means the psychological arrow isn't its own separate thing. It's just a byproduct of the thermodynamic arrow.
Yes.
We are biological machines that consume ordered energy, like food, and turn it into disordered energy, like heat and waste, all to maintain our own internal order. We are basically engines of entropy.
Engines of entropy. I love that. We are surfing the great wave of increasing disorder, and that ride is what we call consciousness or time passing.
So that connects our minds to the broken cup. But what about the third arrow, the expanding universe? Why does the arrow of mess point the same way as the arrow of expansion?
So this gets into the history of the universe. And here Hawking brings up the no-boundary proposal we discussed in a previous deep dive. The idea that the universe started in a very, very smooth, very ordered state.
The Big Bang wasn't a chaotic explosion. It was incredibly uniform.
Exactly. It was small, smooth, and highly ordered. So as it expands, it naturally gets lumpier. Gravity pulls little clumps of matter together to form stars and galaxies. The universe gets more disordered. So for the entire history of the expansion so far, disorder has been increasing.
So the two arrows, expansion and entropy, point the same way simply because of how the universe started. It started neat, and it's been getting messy as it gets bigger.
Yes. But here is where it gets really interesting. And this is where Hawking shows his humility as a scientist. He asks, what if the universe stops expanding?
The big crunch. We've talked about this. If there's enough gravity, eventually the expansion halts and everything comes crashing back together.
All right. And in that contracting phase, the cosmological arrow would reverse. The universe would be getting smaller, not bigger.
So if the cosmological arrow reverses, does the thermodynamic arrow reverse too? Does the arrow of mess flip?
That is the big question. If the universe starts shrinking, do broken cups suddenly come back together? Do people start living backward?
And Hawking admits in the book that he used to think the answer was yes.
It's a wonderful moment of scientific honesty. He had this initial thought that the contracting phase would be just a time reversal of the expanding phase. He thought time itself would run backward.
Can you even imagine that? You'd be born from the grave, you'd get younger, you'd unlearn everything you ever knew, and eventually disappear into your mother's womb.
It sounds like something from a poem, but his colleagues, he specifically names Don Page and Raymond Laflamme, they challenged him on it. They went and did the math on the no-boundary condition for a collapsing universe.
They checked his homework. I love that. And what did they find?
They found that disorder continues to increase. Entropy does not reverse just because the universe starts to shrink.
So even in a big crunch, cups still break.
Yes. The poor astronaut inside a collapsing universe doesn't get younger. They just continue to age until they get crushed into a singularity. Hawking calls it a sticky end.
A sticky end. That's such a typical Hawking understatement. So his initial idea was wrong.
It was. And he admits it freely. The thermodynamic arrow and our psychological arrow do not switch direction just because the universe starts shrinking.
But this raises a problem, doesn't it? If entropy always increases, no matter what, why do we see it aligning with expansion right now? Why aren't we in the contracting phase where entropy is still going up, but the universe is shrinking?
This is where he brings in the weak anthropic principle again.
Okay, remind us what that is.
It's the argument that we observe the universe the way it is because if it were any different, we wouldn't be here to observe it. It's a kind of selection bias.
So we exist in the expanding phase because intelligent life can't exist in the contracting phase.
Not quite. It's more that intelligent life requires a strong thermodynamic arrow to function. We need to consume ordered energy to survive. By the time the universe expands to its maximum size and starts to contract, pretty much all the stars will have burned out. The universe will be in a state of almost complete disorder, a kind of heat death.
Ah, so there's no fuel left for life. There's no order left to turn into disorder.
Exactly. There's no significant energy gradient. There is no order left to consume. The protons themselves might even be decaying by that point. So intelligent beings like us can only exist in this phase, the expanding phase, where there is still a massive difference between the sun, which is hot and ordered, and the cold, disordered emptiness of space.
So we see the arrows pointing the same way because that is the only time we can exist to see them. If we were in the contracting phase, we'd be long dead.
Precisely. The alignment is a necessary condition for our existence.
Okay, let's unpack this. We are stuck with the arrow of time. We're stuck riding this train from the orderly past to the messy future. But humans are stubborn. We don't like being stuck on one track.
Which leads us to the inevitable question. Can we build a loop? Can we travel back?
Time travel. It's been a staple since H.G. Wells, but Hawking takes it really seriously. He starts by looking at whether general relativity, Einstein's theory, actually forbids it.
And surprisingly, for a long time, it didn't seem to.
He mentions Kurt Gödel, right, the famous mathematician.
Yes, Gödel, a friend of Einstein's at Princeton. In 1949, he found a solution to Einstein's own equations, a valid mathematical model of a universe that allowed for time travel.
What did this Gödel universe look like?
It was a rotating universe. If the entire universe were spinning, it would drag space-time around with it in such a way that if you traveled far enough out in a rocket ship, you could find a path that would loop back and you'd arrive before you left.
That sounds incredibly dizzying.
It upset Einstein quite a bit. He really didn't like the idea that his own theory allowed for changing the past. Fortunately for Einstein and for our sense of causality, we have very good evidence that our universe is not rotating.
It's expanding, but it's not spinning, so Gödel's loop is out.
Then there were other ideas. Cosmic strings.
These just sound incredibly cool. Cosmic strings.
Imagine these thin tubes of energy, relics left over from the very early universe. Thinner than a proton, but incredibly dense. We're talking millions of tons of mass in just a millimeter of string and under colossal tension.
Like a rubber band from hell.
An excellent description. Hawking suggests that if you had two of these cosmic strings moving past each other at nearly the speed of light, or maybe one string passing a black hole, they could warp space-time enough to create what's called a closed time-like curve, a loop. You could fly your ship around them and travel back in time.
But do these strings even exist?
We haven't found any. And even if they do, trying to utilize them would be, well, essentially impossible for a civilization like ours. But it showed that the mathematics of general relativity could allow for it.
But there's always the big speed limit, right? The speed of light.
That is the traditional barrier. We know from relativity that nothing with mass can travel at or faster than the speed of light.
I love the little Limerick Hawking quotes here. There was a young lady of white who traveled much faster than light. She departed one day in a relative way and arrived on the previous night.
It's a classic.
Yeah.
And it highlights the problem perfectly. In relativity, space and time are deeply linked. If you could go faster than light, you are technically moving backward in time, according to some observers.
But we can't. As we approach that speed, our mass becomes infinite, and we need infinite energy to push us any harder, so we are stuck.
Unless we cheat.
Cheating is my favorite part of physics. How do we cheat?
We don't travel through space faster than light. We warp the space itself. We take a shortcut.
Wormholes.
Exactly. The Einstein-Rosen bridge.
The visual here is always the folded piece of paper. You draw two dots on a page, point A and point B. The distance is a straight line across the paper. But if you fold the paper over so the dots touch, the distance becomes 0. You just punch a hole through.
That hole is the wormhole. It's a thin tube of space-time connecting two distant, relatively flat regions. You could travel from Earth to Alpha Centauri, which is over 20 trillion miles away, through a wormhole that might only be a few miles long.
So you pop into the wormhole, travel for a few hours, and pop out at Alpha Centauri. Meanwhile, a beam of light taking the long way outside the wormhole takes more than 4 years to get there.
And you've done it. Effectively, you have beaten the light beam. You have traveled faster than light without actually moving locally faster than light at any point. And because of the strange relationship between space and time, if you can do that, you can theoretically travel back in time.
So why don't we have one? Why aren't we commuting to Alpha Centauri for the weekend?
Gravity. Gravity is attractive. It pulls things together. The moment you open a wormhole, the gravity of the universe wants to slam it shut instantly. It would pinch off into a singularity before you could even send a single photon through, let alone a spaceship.
So we need something to prop it open, like a strut in a mine shaft.
Exactly. But normal matter won't work. Normal matter has positive mass and positive energy. It creates attractive gravity, which only helps to close the hole faster.
We need the opposite.
We need matter with negative energy density.
Negative energy. Now that sounds like something a Star Trek writer just made up. Does that actually exist? I mean, energy is stuff. How can you have less than zero stuff?
Surprisingly, yes. It's not just science fiction. Quantum mechanics allows it. To understand why, we have to look at what empty space really is.
We tend to think of it as a vacuum, absolute nothingness.
But quantum mechanics tells us space is never truly empty. It is a boiling sea of what we call virtual particles, constantly popping in and out of existence. Quantum fluctuations.
We talked about this with black holes. It's the quantum foam.
Right. Now imagine that foam is like a sea of waves of all different sizes and energies. Some are tiny ripples, some are massive rollers.
Okay, I'm visualizing the ocean.
Now, you place two perfectly parallel metal plates in that ocean, incredibly close together. This is a real experiment. It's known as the Casimir effect. The gap between them is so small that some of the longer wavelengths, the massive rollers, simply don't fit inside. They are excluded.
Right, like trying to play a really low note on a tiny flute. The sound wave is too long, it doesn't work.
Exactly. So there are fewer virtual particles, fewer quantum waves between the plates than there are outside the plates.
And since we define zero energy as the normal state of empty space outside the plates,
Then the space inside the plates must have less than zero energy. It has a negative energy density.
and we've actually measured this. This isn't just a theory.
Oh yes, we have. Because there are fewer waves pushing from the inside than the outside, the plates are actually pushed together by the vacuum of space. We can measure that force precisely. The Casimir effect is real. Negative energy exists.
So theoretically, if we could harvest enough of this negative energy, and I imagine we're talking about vast, vast amounts, we could use it to thread a wormhole. The negative energy would create a kind of repulsive gravity that pushes space-time apart, keeping the throat of the wormhole open.
In theory, yes. A sufficiently advanced civilization could construct a stable, traversable wormhole, and therefore a time machine, using this principle.
Okay, so the physics says maybe, but my logic says hold on a minute, because as soon as you open the door to time travel, you open the door to all sorts of paradoxes.
Grandfather paradox.
The classic. I build a wormhole. I go back to 1930. I find my grandfather before he has any kids. Well, let's say I prevent him from ever meeting my grandmother.
Yeah.
So my father's never born, which means I am never born. Which means I never build the time machine in the first place. So I never go back to 1930. So my grandfather does meet my grandmother, and I am born, and...
It's a logical nightmare. A loop. It seems impossible. If you exist, you can't exist. If you don't exist, you must exist.
How does Hawking resolve this? Or how do physicists in general try to resolve this?
There are two main schools of thought. The first is what he calls the consistent histories approach.
Which means...
It means you cannot change the past. The past is fixed. If you went back to 1930, you were always there in 1930. Your trip back in time is already part of history.
But what if I try to shoot my grandfather? I have free will, don't I?
According to this view, something will stop you. The gun jams. You slip on a banana peel. You miss. Or it turns out the man you shot wasn't your real grandfather. The universe, the very laws of physics, conspired to ensure consistency.
That sounds terrifying. It implies I have no free will. I'm just an actor following a script that's already been written for all of time.
Hawking acknowledges that. It's a very disturbing thought. He says that while we feel we have free will because we can't predict our own future, in a time travel scenario, the future, your arrival, is already part of the recorded past.
Yeah.
So your actions are constrained. You physically cannot create a paradox.
I hate that. Give me the other option, please.
The other option is the alternative histories hypothesis. This is basically the Back to the Future model.
Marty McFly.
Right. If you go back and you successfully change something, space-time branches. You create a new timeline. You haven't changed your past. You've just created a different future for that new branch of the universe.
So in timeline A, I wasn't born, but I still exist because I came from timeline B, where I was.
Yes. Hawking notes that this aligns somewhat with Richard Feynman's sum over histories concept in quantum mechanics, the idea that the universe takes all possible paths. However, Hawking himself tends to lean toward the consistent histories view for big macroscopic objects like people. He thinks the universe probably doesn't like making those big, messy branches.
There is one argument against time travel that seems pretty damning, though. Hawking brings it up, and it's the one everyone always asks. The tourist argument.
Where are the tourists?
Exactly. If time travel is ever discovered in 100 years, 1,000 years, a million years, why haven't we been overrun by people from the future coming back to watch the pyramids being built or to see the Beatles play live?
It is a very strong point. The absence of future visitors strongly suggests that either they never figure it out or there's some fundamental law preventing them from coming back to our time.
Maybe they're here and they're just really, really good at hiding. Or maybe UFOs, they're just us from the future in our time-traveling minivans.
Hawking dismisses that with his characteristic wit. He suggests that if they were here, they'd probably be much more obvious and, frankly, unpleasant. But more importantly, he thinks physics might have a built-in defense mechanism.
A defense mechanism? What kind?
He proposes something he calls the chronology protection conjecture.
That sounds like a time cop agency from a movie.
It's sort of the universe's version of that. Hawking suggests that the laws of physics themselves actively conspire to prevent macroscopic time travel.
How? Does the universe just say, no, you can't do that?
It's more clever than that. Think about the wormhole again. You have a loop that allows you to go back in time.
Okay, got it.
Now imagine a single particle of light, a photon, entering that loop. It travels back in time, comes out before it entered, and then it can enter the loop again.
And then it travels back again and enters the loop again.
It loops infinitely. It's exactly like putting a microphone next to a speaker. You get that screeching feedback loop.
Oh, right. The sound gets amplified over and over and over until it just blows the speaker.
It's exactly the same principle. In the wormhole, the energy of these looping virtual particles from the quantum foam would build up infinitely and instantaneously.
And an infinite buildup of energy means...
It means the wormhole collapses or explodes. The feedback loop of radiation destroys the time machine the very moment you try to turn it on.
So the universe protects itself. It burns the bridge before you can even cross it.
That is the conjecture. It seems that while the laws of general relativity might allow for the geometry of time travel, like wormholes, the laws of quantum energy dynamics, like the radiation feedback, might prevent it from ever actually working for anything larger than a subatomic particle.
But you mentioned subatomic particles. Does time travel happen on the micro scale?
Oh, absolutely. And we see it all the time in particle physics. Feynman diagrams, which are the little stick figure maps we use for particle interactions, often interpret antiparticles as being normal particles just moving backward in time.
Wait, really? So an antimatter positron is, from one point of view, just a regular electron going backward through time.
Mathematically, they are completely equivalent. And remember the black hole radiation we talked about, Hawking radiation.
Yes, the particles that seem to escape from a black hole.
One way to visualize that entire process is to see a particle falling into the black hole, traveling backward in time for a bit, and then getting scattered out as a new outgoing particle. So on the quantum level, the distinction between past and future is very, very blurry.
It's wild to think about. Down at the pixel level of reality, time is jumping back and forth constantly. But up here, where we live, we are stuck flowing steadily toward the future.
Protected, perhaps, by the chronology protection conjecture.
It feels like a bit of a letdown in a way, but also a relief. I don't have to worry about accidentally deleting my own existence.
It also gives a certain weight to our actions. If we can't just go back and undo them, they matter.
So let's wrap this up. We've covered a lot of ground here.
We certainly have. We've seen that the arrow of time, the reason we age and our coffee gets cold, is driven by entropy. The universe is fundamentally moving from a state of order to disorder.
And we've learned that our very ability to remember the past is a product of that disorder. We have to burn energy and create heat to store memories.
And we've seen that while general relativity tantalizingly offers the possibility of wormholes and time loops, the universe seems to fight back with things like radiation feedback loops and the immense challenge of negative energy.
It seems the universe is pretty determined to keep its timeline straight.
For now, at least.
Yeah.
As Hawking always reminds us, we still don't have the full picture. We don't have the complete quantum theory of gravity. Until we unite those two great theories, the final verdict on time travel is still, well, it's pending.
And that is a perfect segue. We have looked at the very big, which is relativity, and the very small, which is quantum mechanics. We've seen how they clash over things like black holes and the possibility of time travel.
They are the two halves of our map of reality, but they don't quite fit together at the edges.
In the final part of our series, we will look at the ultimate goal of science. A single theory for everything in the unification of physics and the conclusion.
The search for the master keys can be a great discussion.
I can't wait. But before we go, I want to leave you with a thought from this deep dive. Hawking says the universe protects the past, the chronology protection conjecture. The past is safe, it's fixed.
But the future.
We assume the future is open, unwritten, but if that consistent history's view of time travel is right, if the timeline must be consistent to avoid paradoxes, is the future just as fixed as the past? Are we just discovering the script as we read it aloud?
That is a thought to mull over while you try not to break any cups. Imagine for a second that you are Albert Einstein. You have just completely revolutionized how humanity understands gravity, space, and time. You are the most famous scientist in the world. You are literally the personification of genius. But for the last 30 years of your life, you are frustrated. You're searching for something, a single elegant key that unlocks the entire universe, and you just can't find it.
It is, it's the ultimate unrequited love story of physics. Einstein spent his final decades hunting for a unified field theory 1 single framework that would stitch together the grand laws of gravity with the strange, jittery world of electromagnetism and quantum mechanics.
And he never got there.
He never found it. He died with a notebook full of equations that didn't work.
But the dream didn't die with him. In fact, the search for this holy grail of physics became the driving force of the entire field. And that is exactly where we are going today.
The final frontier.
Welcome to the conclusion of our series on A Brief History of Time. Today, we cover the unification of physics and Hawking's final philosophical thoughts.
It's been quite a journey, hasn't it? I mean, we've gone from turtles all the way down to black holes that aren't actually black, and now we're really at the edge of the map.
We certainly are. Welcome to Fact Horizon. We take a stack of your sources, articles, research, your own notes, and extract the most important nuggets of knowledge or insight.
Think of it as a shortcut to being well-informed, with surprising facts and just enough humor to keep you hooked.
I'm your host, and today we are tackling the really big questions: string theory, extra dimensions, the mind of God, and the ultimate question of why we are here at all.
It is the heavy-hitting stuff. We are, in a way, trying to finish what Einstein started.
So let's unpack this. The goal is a theory of everything. But before we get to the strings and the weird dimensions, we have to talk about the failures. Because apparently physicists have this habit of thinking they're almost done right before they hit a massive wall.
They absolutely do. It's a recurring theme in the history of science. You could call it the false dawn phenomenon. You get this feeling that the puzzle's almost complete. You just need to slide in the last few pieces of sky, and you can go home.
There's a great story in the source material about Max Born.
Right, Max Born, a Nobel Prize winner, a truly brilliant physicist. So in 1928, he's at Göttingen University, and he tells a group of visitors, and I'm paraphrasing here, physics as we know it will be over in 6 months.
6 months? That is an incredible amount of confidence. I wouldn't even commit to finishing a book in 6 months, let alone solving the entire universe.
It's just staggering confidence, but you have to see it from his perspective. A physicist named Paul Dirac had just discovered the equation that beautifully described the electron.
Okay.
So Born's thinking was, okay, we have the electron. The only other particle we really know about is the proton. We'll find a similar equation for that, wrap it all up with a bow, and be done by Christmas.
And what happened?
Well, and then the neutron was discovered. And then they found the strong and weak nuclear forces. And suddenly, the picture wasn't this simple, elegant little duet anymore. It was a chaotic, messy orchestra with instruments nobody had ever seen before.
It reminds us that whenever we think we have the universe in a box,
The universe punches a hole in the side of the box, yes.
so the finish line just keeps moving. But the biggest hurdle, the one that really stumped Einstein and everyone since, is this fundamental clash we've touched on before, the clash between general relativity and quantum mechanics. Why can't they just get along?
Because they speak fundamentally different mathematical languages, and they describe reality in ways that are, on the surface, totally contradictory.
Okay, break that down for us.
General relativity, which is Einstein's theory of gravity, it handles the big stuff, planets, galaxies, the curvature of space-time, and it assumes that space-time is fundamentally smooth, like a rubber sheet. You can curve it, warp it, stretch it, but it's continuous.
Like a classic trampoline analogy.
A bowling ball and a trampoline. Exactly. But quantum mechanics, which handles the tiny subatomic world, says that if you look closely enough, nothing is smooth. Everything is granular, it's chaotic, it's governed by probabilities and the uncertainty principle.
So it's not a smooth trampoline, it's more like a pixelated screen,
Yeah.
where if you zoom in enough, you see the individual dots.
That's a great way to think about it. And the real catastrophic problem arises when you try to apply both theories at the same time, especially on those very, very tiny scales.
And this has to do with those virtual particles we talked about in a previous deep dive.
Precisely, remember those. The idea from the uncertainty principle that empty space isn't empty at all. It's fizzing with these pairs of particles and antiparticles that pop into existence from nothing and then, a fraction of a second later, annihilate each other.
They're like little ghosts, appearing and disappearing constantly.
Everywhere, all the time. Now, if you try to apply general relativity to that fizzing, chaotic quantum foam you run into, well, you run into an infinity catastrophe.
A catastrophe sounds bad.
It's about as bad as it gets in physics. You see, these virtual particles, for the brief moment they exist, they have energy. And according to Einstein's famous equation E equals mc squared, energy has mass. And mass, of course, creates gravity.
Oh, I think I see where this is going. It's a domino effect.
It's a terrifying domino effect. If you have an infinite number of these fluctuations happening at the tiniest scales, you technically have infinite energy.
Which means infinite mass.
Which means infinite gravitational attraction.
So what would that do?
It would mean that every single point in space has an infinite gravitational pull, which would have caused the entire universe to curl up into an infinitely small, infinitely dense ball a long, long time ago.
Which I've noticed has not happened.
Correct. We are still here. So the math, it just blows up. It gives you infinities as the answer to your calculations. And in physics, if your equation spits out the word infinity, it's basically the universe's way of screaming at you that your theory is broken.
So you can't just mash the two theories together. The math literally falls apart.
It does. And for a long time, scientists tried to find clever ways to, cancel out these infinities. There was a big attempt in the 1970s called supergravity.
Supergravity. Sounds like something out of a bad superhero movie.
It does, but it was a very serious and very clever idea. The thought was maybe every particle has a superpartner particle, and maybe you can pair them up in such a way
that their effects cancel out.
Exactly. The idea was that the positive energy contributions from some virtual particles would be perfectly canceled out by the negative energy contributions from their superpartners. It was about balancing the cosmic books.
Did it work?
The answer is maybe. The problem was that the mathematics involved was so horrifyingly complex that nobody could actually solve the equations.
Really?
Yeah. Hawking mentions in the book that to check if all the infinities truly canceled out, the calculations would be so long that it would take a single person about 4 years to do them by hand. And you would almost certainly make a mistake somewhere along the way.
So they had a potential solution they couldn't even test.
They were stuck, completely stuck. They needed a paradigm shift, a totally new way of looking at the fundamental nature of reality. And this is where it gets really interesting. This is where we enter the world of string theory.
Okay, the big one.
Yes, this is the big pivot. Up until the 1980s, we always thought of fundamental particles, electrons, quarks, photons as points. Tiny, zero-dimensional dots.
Like a period at the end of a sentence, but infinitely smaller.
Right. But in 1984, the wind changed direction. A group of physicists started asking a radical question. What if they aren't dots? What if the fundamental building blocks of the universe aren't points at all, but tiny, vibrating strings of energy?
Strings. So instead of a dot, you have a little snippet of thread.
Think of them as one-dimensional objects. They have length, but no thickness, no width. They're infinitely thin. And just like a violin string can vibrate at different frequencies to produce different musical notes.
A low C, a high G.
These cosmic strings vibrate at different frequencies to create different particles. It's an incredibly beautiful idea.
So an electron is just a string vibrating in one particular pattern. And a quark is the same kind of string, just vibrating in a different pattern.
Exactly. And a photon is another vibration, a graviton is another. All the different particles and forces we see in the universe are nothing more than different notes being played on these fundamental strings. The symphony of the universe is, well, it's literally a symphony.
That is a very elegant idea. But more importantly, does it solve the infinity problem?
It does. And the way it does it is, again, very elegant. It helps to visualize how these things move through time.
Okay.
If you have a particle, a point, a dot moving through our 4 dimensions of space-time, it traces out a line. We call that a world line.
Right. A dot moving through time makes a line. I can picture that.
But now what if you have a string, a little one-dimensional line? What happens when it moves through time?
It would trace out a surface, like a ribbon.
Exactly. We call that a world sheet. A point particle creates a world line. A string creates a world sheet. An open string with two ends traces out a strip, and a closed string, a loop, traces out a tube or a cylinder as it moves through time.
So dot makes a line, and a line makes a ribbon or a tube. Got it.
Now, think back to the problem. When two-point particles interact, say, they collide and merge, their two world lines come together at a single, sharp point.
A vertex.
A vertex. And that sharp, infinitely small point is where the math goes haywire. That's where the infinities happen. It's like a singularity in the interaction, a traffic accident at a single point.
Okay, so how does the string picture fix this?
With strings, you don't have lines meeting at a point. You have two tubes floating towards each other and merging. They don't meet at a sharp point. They join smoothly.
Like the legs of a pair of trousers merging into the waist.
Yeah. That is the exact analogy Hawking uses. He talks about it like plumbing. Instead of a sharp, jagged collision, you have a smooth piece of plumbing. Two pipes merging into one. The interaction that describes one particle emitting a force that affects another, like an electron emitting a graviton, looks like an H-shaped tube.
An H shape.
Yeah, imagine two vertical tubes, the two original strings moving through time, and they're connected by a smooth horizontal tube. That horizontal tube is the interaction, the force carrier, because the whole thing is one continuous smooth surface. The singularity, that point of infinite density, is smeared out. It's gone.
So the infinities just disappear.
They vanish. The math works. It's an incredible breakthrough.
That sounds perfect. Like a problem solved. Einstein would have been thrilled. But
What?
I feel like there's always a but in these stories.
There is always a but. String theory is beautiful, but it comes with some very, very strange baggage.
Heavy baggage.
Extremely heavy. For one thing, the tension on these strings has to be unbelievable. Hawking mentions that this isn't like a guitar string. For these strings to represent gravity correctly, they would need a tension of about 1,000 million tons.
I can't even comprehend that number.
It's a 1 with 39 zeros after it. We're not talking about rubber bands here.
Okay, so they're incredibly stiff. What's the other piece of baggage?
The other piece of baggage is even stranger, and it's the one that everyone always asks about. For the mathematics of string theory to work, for all the vibrations to behave properly, and for the problematic anomalies to cancel out, the universe cannot have just 3 dimensions of space and 1 of time.
Oh boy, here we go.
The math demands that space-time must have 10 dimensions, or in some of the earlier versions of the theory, 26.
Okay, let's stop there. I am looking around this room. I see forward, backward, I see left, right, and I see up, down. That is 3. I have a watch. That's time. That's 4. Where on earth are the other 6? Or the other 22?
That is the obvious and perfectly reasonable question. If string theory is right, where are these extra dimensions hiding? Why don't we trip over them when we walk down the street?
Exactly.
The most popular answer is that they might be curled up.
Curled up. What does that mean?
The analogy often used is to imagine a garden hose or maybe a long power cable lying on the ground. From a long way away, if you're in an airplane looking down, it just looks like a one-dimensional line. It only has length. You can't perceive its thickness at all.
Right, it just looks like a line drawn on the grass.
But if you walk up close to it, or more to the point, if you are an ant crawling on its surface, you realize it has a second dimension. It has a circular cross-section. You can go forward and backward along the length of the hose, but you can also go around the hose.
So the idea is that the familiar dimensions, or 3 dimensions of space, are like the long, flat direction of the hose. They're big and obvious.
Yes, and the extra dimensions are like the tiny circular part of the hose. They are curled up on themselves so tightly on a scale 1,000 million times smaller than a centimeter that we simply cannot see them or move through them.
We're too big. We're like the airplane, not the ant. We're stuck moving in the big flat dimensions.
That's the idea. We're confined to our 4-dimensional brain, a slice of a higher dimensional reality, and we can't perceive those tiny curled up directions.
That is wild, but why? Why would the universe have some dimensions that are huge and expanding and others that are curled up into these tiny little balls? Is it just random?
Well, this is where Hawking brings in the anthropic principle again. He argues that there might be a very good reason we find ourselves living in a universe with exactly 3 large, perceptible spatial dimensions.
Let me guess. Because if it were any different, we wouldn't be here to notice it.
You've got it. It's a selection effect. Let's just think about what would happen if you had, say, more than 3 large spatial dimensions. Imagine a 4D space. The laws of gravity would be different. In our 3D world, the force of gravity follows an inverse square law. If you double the distance from an object, its gravity gets 4 times weaker. It spreads out over the surface of a sphere.
Right.
In a 4D world, it would follow an inverse cube law. Gravity would drop off much, much faster with distance. It gets diluted across more dimensions.
And what's the consequence of that?
The consequence is that stable orbits become impossible. The Earth wouldn't be able to maintain a stable orbit around the sun. It would either spiral into it and burn up, or it would fly off into the cold, dark void.
And the same for electrons around an atom.
Exactly. Electrons couldn't maintain stable orbits around the nucleus. Atoms, as we know them, couldn't exist. Matter couldn't form. No stars, no planets, no people.
So in a universe with 4 big spatial dimensions, there's no structure. It's just chaos. Okay, so what about fewer dimensions? What if we lived in a 2D world, like a flat sheet of paper?
That presents a different set of problems, especially for complex biology. Hawking points out a very practical, almost funny issue. Think about any complex organism. It needs to process food. It needs a digestive tract, basically a tube that runs from a mouth to, well, to the other end.
Yeah.
In a 3D creature like us, that tube runs through our body, but our body remains connected all around it. In a 2D creature, a flat creature on a page, a tube going all the way through it, would literally cut the organism in half.
Oh, I see it now. In 2D, a line that goes all the way through a shape divides it into 2 completely separate pieces. There's no way to go around the digestive tract.
You just fall apart into 2 halves. So complex mobile life with a flow-through digestive system seems impossible in 2D.
So we're in the dimensional Goldilocks zone. 2 dimensions is too simple for complex biology. 4 or more is too unstable for gravity and atoms. 3 is just right.
That's the anthropic argument. We observe 3 large spatial dimensions because it's the only configuration out of all the possibilities allowed by string theory where intelligent beings could evolve to ask the question in the first place.
So string theory gives us this 10-dimensional framework, but 7 of them are curled up, leaving us with the 3 that we need to exist. But then, as always, things got even more complicated, didn't they? It turned out there wasn't just one version of string theory.
No, not at all. By the late 1980s and early 90s, physicists were actually a bit embarrassed. They had set out to find the one unique theory of everything, and instead they had found 5.
5 different string theories.
Yes. They had different assumptions, different symmetries. Some had only closed loops of strings, some had open strings. It seemed like the quest for unification had led to, well, fragmentation. The theory of everything was actually the theories of 5 things.
Which is not very unified.
Not at all. It was a major disappointment. But then came what's often called the second superstring revolution, around 1994. And the key discovery was something called dualities.
Dualities. This is the idea that different theories are actually describing the same underlying reality, just from different perspectives.
Exactly. It's a profound concept. Physicists started discovering that if you took string theory A and you looked at it under certain conditions, say with very strong forces, it turned out to be mathematically identical to string theory B under very weak forces. They were just 2 different descriptions of the same physics.
So there weren't 5 competing theories, they were 5 different windows into the same room.
Precisely. And this also led to the realization that strings aren't the only game in town. The theories also predicted the existence of other objects called p-branes.
P-branes.
Yeah, where p just stands for the number of dimensions the object has. So a 0 brane is a point, like an old-fashioned particle. A 1 brane is a string. A 2 brane is a 2-dimensional membrane, like a surface. But you could have p-branes with 3, 4, up to 9 dimensions.
So the universe isn't just filled with vibrating strings, but also vibrating membranes and multidimensional blobs.
It seems so. And all these different theories, the 5 string theories and another one called supergravity, they all seem to be different aspects of a single underlying 11-dimensional theory that no one fully understands yet. They call it M theory.
M theory. What does the M stand for?
Nobody's quite sure. It could be for master, mother, mystery, or membrane. The joke is that the M will be decided once we actually figure out what the theory is.
Okay, so this realization that there isn't one neat theory, but this whole web of connected ideas, it led Hawking to a very deep conclusion about the nature of the ultimate theory itself.
It did. For a long time, the dream was to find a single elegant equation. Something like E equals mc squared, but for everything. A formula you could print on a t-shirt and say, this is it, these are the laws of the universe.
And Hawking says that whole dream might be misguided.
He suggests that there might not be one single formulation. And he uses this brilliant map analogy to explain it.
The map analogy.
Think about mapping the Earth. It's a sphere. You cannot represent the entire surface of the round Earth on a single flat piece of paper without some kind of distortion.
Right, like the Mercator projection maps we see in school. Greenland looks as big as Africa, which it isn't.
Exactly. The shapes and sizes get distorted, especially near the poles. So to map the whole Earth accurately, what do you need? You need a collection of maps, an atlas. You have one map for the North Pole, another for the equatorial regions, another for the South Pole. Each map is accurate in its own little patch.
And where the maps overlap, they agree with each other.
Precisely. Where they overlap, they describe the same bit of Earth consistently. But no single flat map can cover the whole thing perfectly.
So Hawking is suggesting the theory of everything might be like that atlas.
Exactly. It might be a collection of overlapping theories, the different string theories, supergravity, P-branes, that are all valid in their own domains, in their own patches of reality. They agree where their domains overlap, but no single one of them is the one true master theory that describes everything.
That is a huge shift in perspective. It's like giving up on the dream of the God equation and accepting a God atlas instead.
It is. He calls it a democracy of theories. No single theory is more fundamental than the others. They're all just different reflections of the same underlying reality, which might be too complex to be captured by a single human formulation.
Wow. Okay, so we have gone from point particles to vibrating strings and membranes, from 3 dimensions of space to 10 or 11, and from searching for a single equation to this idea of a whole network of theories. It's a lot to take in.
It is an incredible amount to absorb, and I think this is the perfect moment to pause and just look back, because this is the final deep dive of our series on a brief history of time. We should really take a moment to appreciate the full arc of the journey Hawking has taken us on.
That's a great idea, because when you stack it all up like that, the intellectual leap that humanity has made, especially in the last century, is just staggering.
Think about where we started this whole series. Chapter 1, The Tower of Tortoises.
The old story about the scientist giving a lecture and the old lady in the back saying the world is a flat plate on the back of a giant turtle and it's turtles all the way down.
In Aristotle, we started with the idea that the Earth was the absolute center of everything, that it was stationary, eternal, the natural state of any object was to be at rest.
And then came Galileo and Newton, and they just shattered that whole picture. They proved that universal laws, not local whims, govern motion. The same gravity that makes an apple fall also holds the moon in orbit.
But even with Newton, we still clung to some absolutes. We had absolute space and, most importantly, absolute time. Time was seen as this universal clock ticking at the same rate for everyone, everywhere, a railway track that ran straight and true regardless of what happened in the universe.
Until Einstein came along and blew up the railway tracks.
Completely dismantled them. He showed us that time is personal, it bends, it stretches, it slows down. Space is flexible. Gravity isn't some mysterious force reaching across the void, it's the curvature of space-time itself. That was the death of absolutes.
And just as we were getting our heads around that, Hubble looked through his telescope and showed us that the universe isn't a static painting on the ceiling. It's an explosion happening in slow motion. It's expanding.
Which implies a beginning. The Big Bang. Suddenly the universe had a history. But just when we thought we had this grand, deterministic cosmic story figured out, quantum mechanics walked in and destroyed determinism itself.
Right. Heisenberg's uncertainty principle.
The idea that nature, at its most fundamental level, has an inherent randomness to it. You can't know both the exact position and the exact momentum of a particle. The dream of a perfectly predictable, clockwork universe Laplace's dream was over.
So we lost the center of the universe, we lost absolute time, and then we lost the ability to predict the future with perfect certainty.
And then Hawking himself took us into the heart of his own work. He took us into the black hole, the ultimate prison of gravity, and showed us that even these darkest of objects aren't truly black, and they aren't eternal prisons.
They grow. They leak radiation. Black holes ain't so black.
And they evaporate over trillions of years, which led to the wildest idea of all, the one we discussed in the last deep dive, the no-boundary proposal. The idea that the universe, when viewed in imaginary time, is like the surface of a sphere, finite in size, but with no beginning, no end, no edge, no moment of creation. It just is.
It's a breathtaking trajectory. From a flat Earth on a turtle to a 10-dimensional, self-contained, vibrating brain world that needs no outside boundary to exist.
It really makes you appreciate how far we've come in just a few hundred years of systematic thought. But this brings us to the final and perhaps the most important part of the book, the conclusion, Chapter 12.
The mind of God. This is where Hawking stops being just a physicist and becomes a philosopher.
He pivots from the how to the why. After laying out this incredible scientific picture, he asks, okay, so what is the nature of this ultimate theory we're looking for? What are the possibilities?
He lays out three options for the future of science, right?
Right. Possibility one is the optimistic one. A complete, consistent, unified theory exists, and we are capable of finding it.
Possibility two.
Possibility two is that there is no final theory, that there's just an infinite sequence of better and better approximations, like Russian nesting dolls of theories that go on forever. We'd never find the bottom.
And possibility three is the most bleak.
It is. Possibility three is that there is no theory at all, that events in the universe beyond a certain point are not governed by laws. They are fundamentally random and arbitrary, that we hit a wall where things just happen for no reason at all.
Hawking pretty much rejects that third one out of hand, doesn't he?
He does. He basically argues that the entire project of science is based on the assumption that the universe is not arbitrary. If it were, science wouldn't work. But he also argues against the second one, the infinite sequence of theories. He thinks there is a limit.
The Planck energy.
Exactly. We talked about this. Because gravity becomes so incredibly strong at extremely high energies, the so-called Planck scale, it basically walls itself off. Any attempt to probe smaller scales would require so much energy that you'd just create a tiny black hole that swallows your experiment. There seems to be a fundamental limit to how small we can look.
Which suggests that the boxes within boxes have to stop somewhere. There is a bottom layer.
So he lands firmly on possibility one. He is an optimist. He thinks we will find it. He even says there's a good chance we'll find a complete unified theory within the lifetime of some of us alive today.
He adds a pretty important caveat, though.
He does, assuming we don't blow ourselves up first.
Always a valid concern. But here's the part of the conclusion that really struck me. Hawking talks about the growing gap between the scientific specialists and the rest of us.
This is such a crucial point for him. He looks back to Newton's time when an educated person could, in principle, understand the entirety of human scientific knowledge. It was accessible.
But now you need a PhD in advanced mathematics just to understand the titles of the research papers in theoretical physics.
Exactly. Science became hyper-specialized and technical. It left the philosophers and the public behind. And Hawking makes this very biting critique of modern philosophy. He says philosophers used to ask the biggest questions. Plato, Aristotle, Kant, they studied the whole of human knowledge.
But now, he says, they've mostly restricted themselves to just the analysis of language.
Yeah, he quotes Wittgenstein's famous statement, "The sole remaining task for philosophy is the analysis of language." And Hawking's response is basically, what a come down from the great tradition of philosophy.
This is a sick burn from a physicist.
It is. But his point is not just to criticize. His hope is that if and when we find this unified theory, it won't stay buried in arcane mathematics forever. Eventually, its core principles will be digested, simplified, and taught in schools.
So that everyone, not just the wizards in the ivory tower, can understand the fundamental laws that govern our existence.
And that leads directly to his final, most profound, and most provocative question, the question of why.
This is the quote that always gives me chills. He says, even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe?
It's just a beautiful and haunting question. You can have the perfect blueprint for a house. The math is perfect, every angle is right, the structure is sound. But the blueprint is not the house. What is the force, the impetus that makes the blueprint become a physical reality? What breathes fire into it?
He's asking, why does the universe go to all the bother of existing?
It's the ultimate metaphysical question. For their entire history, scientists have been focused on how. How does the sun burn? How do planets move? Hawking, at the end of his book, dares to ask, why?
And this inevitably touches on the role of a creator, of God. We talked about this when we discussed the no-boundary proposal. If that proposal is right, the universe has no beginning in time. It wasn't created at a specific moment.
Right. If the universe is completely self-contained, like the surface of the Earth, it creates a theological problem. If there was no moment of creation, what is there for a creator to do? You don't need someone to light the fuse if there is no fuse.
Hawking says God would have had no freedom to choose how the universe began because it didn't begin in that traditional sense. The laws of physics determined its state.
But, and this is the crucial nuance he adds, God might still have had the freedom to choose the laws themselves.
The law of physics.
Exactly. Why these laws? Why a 10-dimensional string theory? Why quantum mechanics with its uncertainty principle? Even if the universe is a self-contained system that runs on its own logic, you still have to ask, who or what chose the logic?
So the role of the creator shifts from being the first mover who kicks things off to being the author of the logic, the great mathematician.
Or the one who breathes the fire into the equations? Hawking even speculates that maybe there is only one possible set of laws that is logically self-consistent and also allows for the existence of complex structures like us. Maybe God didn't have a choice in the laws either if the goal was to create beings capable of asking these very questions.
Which brings us right back around to the anthropic principle. We are here, therefore the laws must be such that they allow for us to be here.
It's a fascinating logical loop. But Hawking's final thought is one of profound inclusion. He says that the goal of humanity should be to find this theory. And when we do, it shouldn't be the private property of scientists. Everyone, philosophers, scientists, ordinary people on the street should be able to take part in the discussion of why it is that we and the universe exist.
And if we find the answer to that,
If we find the answer to that, it would be the ultimate triumph of human reason, for then we would know the mind of God.
the mind of God, it's just an incredible, powerful way to end a book on cosmology.
It is. It bridges the gap between the cold, hard mathematics of physics and the deep, warm human yearning for meaning. It asserts that our reasoning power, the thing that lets us do calculus and build telescopes, is ultimately capable of grasping the deepest truth of existence.
It's fundamentally an optimistic statement. It says we aren't just specks of dust in a random, meaningless void. We are specks of dust that can figure out the rules of the void.
And perhaps by figuring out the rules, we can begin to understand the purpose of the void.
Well, on that note, we have reached the end of our very long journey through a brief history of time. We've traveled from the very small to the very large, from the beginning of time to the end of time, and into dimensions we can't even see.
It has been an absolute pleasure unpacking it all. It really does change how you look up at the night sky.
It really does. It feels less like a static, painted backdrop and more like a living, vibrating, expanding, curved mystery that we are just on the verge of solving.
A mystery with no boundaries.
I want to leave our listeners with one final provocative thought to mull over, something that builds on what we just discussed.
Go for it.
If Hawking is right, and the universe is finite but has no boundary, if it is completely self-contained and just is, and if we eventually find that one unified theory, or that atlas of theories that describes it perfectly, does that set of equations also describe us? Our thoughts, our consciousness, our curiosity, our very desire to know the mind of God, just incredibly complex variables churning away inside that same cosmic equation.
That is a thought that will keep you up at night. Are we simply the universe's way of thinking about itself?
I think we just might be. Thank you for joining us on this incredible series here on Fact Horizon. Keep looking up and keep asking why.
Goodbye, everyone.